chemistry topic, what I have been doing and what I will do. So my research area is mainly focused on different aspects of organic synthesis and catalysis. Here you can see, during my PhD, I mostly work on the functionalization of carbonyl compounds, where the range of transformations such as CH alkylation, CH hydroxylation, as well as peroxidation, we have performed using earth abundant metal catalysis. And to continue that, we just move for the rearrangement of different peroxides. Out of this, what I'm going to do, I will take the CH peroxidation work, and that I will discuss briefly. After that, so sorry for this slide I made different, but this looks like very ugly here. It should not be the black things. I not made like this, but due to some technical things, it's showing like this. So sorry for that. So during my postdoc, I work on different projects. It ranges from the immobilization of organocatalysts. So also I have been working on the asymmetric carbonyl in a reaction from the Max Planck, and the current work, which is the photoflow hydrolysis, which is one of the fundamental work we recently completed. And I'm going to talk on this photoflow hydrolysis of furans also. So first I will discuss the photohydrolysis work. So if you see the modern organic synthesis or carbon-containing compounds, they generally originate from the fossil chemicals. And 85 to 90% of the chemicals what we use, which is coming from the fossil containing origins. However, the bio-based compounds, which only constitute to the 10 to 15%. Here, one thing we need to keep in mind that if we compare these two things, like a fossil base versus bio-base, then if you see the cost for the fossil-based compound is cheaper, but for bio-based compound is slightly higher on side. Also, the environmental impact from coming from the fossil fuels or fossil compounds, which is very high, and it generates a lot of CO2. As contrast to that, if you use a bio-based compounds, which will give the less amount of CO2 release. And if you want to achieve the mission of net zero by 2050, we have to consider the bio-renewable resources. But the problem is the scalability of the bio-based compounds is slightly lower. The challenge is not just replacing the molecule, but the scaling the supply chain to match the fossil efficiency. That's why if we say we have to replace the fossil things with the bio-derived compound, but first we have to make sure that we should have a sufficient supply of those starting materials. So for that reason, what we did a fundamental discovery in by utilizing the furan-based compound. Here you can see the lignocellulose, such as hemicellulose or cellulose, are the initial starting material, which gives the different furanoids, such as furan. Then we have the furfural as well as HMF, which is a common solvent in industry. However, if you want to convert them into some valuable compounds, such as the butyrolactone, which is one of the starting material in polymer industry, we have to go via, you can see on the top portion, which is marked in a red arrow, oxidative. Here we need to use some oxidant in order to get some acid and then again reduce it to get the butyrolactone. If we use the other approach, we have to do first reduction and then we have to go towards oxidation. So we cannot avoid these two steps. So for that reason, what we came up with our solution, how about we do the redox neutral reaction, where we are not going to use any oxidation or reduction, and the reaction will proceed via simple redox chemistry. If we want to do the defossilization, we have to shift from the petroleum base toward the bio-based derived compound, because the fossil source they constitute, such as the butadiene or acetylene, they need to undergo several reactions in order to get the final compound. For instance, I have shown this reaction where at the bottom you can see the succinaldehyde is the main product which is obtained from the 5 steps, and atom economy for this transformation is very poor. How about we do this transformation from bio-derived furan in one step? It will be atom economical, pot economical, and redox economical. So this will have all the features. I think the slides are not going in that direction. Is it possible to connect the laptop? आगे कहीं चालू है पण ठीक आहे याच्यात पण चालेल आहे. आता येईल हा ओके सर ठीक आहे. Okay, so sorry for this disturbance. And so we are on this slide where we know the furan, which is a 5-member heterocycle, aromatic in nature, highly electron rich, and it can be obtained from the bio-derived biosources. Also, the problem of the furans, most of the time it undergoes a polymerization reaction in presence of acid or under heating. So if you want to synthesize the furan, we use the classical name reaction or simple reaction, which called a Pal-Nor synthesis. However, can we do the reverse of this reaction? Or we can call it a retro-Pal-Nor reaction, where we take the furan and directly we get the succinaldehyde. However, there is one fundamental problem and challenge in this reaction. Once we treat the starting material or the form product, if we get, then it's highly sensitive towards the heat and acid, and then it will rapidly undergo depolymerization or decomposition. So for that reason, we thought to use the approach of photochemistry. So here, if you see the property of furan or reactivity of furan, then on the downside, you can see when the furan is substituted at 2nd and 4th position, then that reaction is very easy. We can get that the product of that reaction will be a 1,4-diketo compound, which is very easy to perform, because this reaction undergoes via a spontaneous way. However, if you want to do the reaction of simple furan or 2-substituted furan, then the reaction is non-spontaneous and it needs some amount of energy. So for that reason, due to the high demand of energy, we thought to utilize the process of photochemistry. For that reason, we have chosen the photocatalyst, which is organic photocatalyst, which does not contain any metal, and it mitigates the retro-Pal-Nor reaction. How it works? We simply use the 450 nanometer light source, and in presence of mixture of acetonitrile and water, we get an intermediate. You can see that highly strained and 10-member intermediate, which we call 1,6-dioxazine. To perform this retro-Pal-Nor reaction, we need the hydrolytic equilibrium between the succinaldehyde or intermediate to furan. So the main reason why we don't get the polymerization in this reaction is due to the formation of this 10-member intermediate. This stops the polymerization and it simply undergo hydrolysis to give the 1,4-diketo compound or succinaldehyde. So similarly, on the right side bottom, you can see the furfural, which undergoes the photocatalytic reaction, and it gives a Piancatelli type rearrangement. So this type of reaction, the feature is it's 100% economical because we are simply using the water to just break up this ring. After extensive optimization for solvent, temperature, catalyst, as well as equivalents of water, we could able to get this transformation in very decent yield. You can see this a fancy molecule which we call a mesh acridinium photocatalyst. You can see its charge complex and it's stabilized by the counter anion, which is BF4. So when we excite this molecule with the photolight, it undergoes some kind of excitation and it goes via a radical mechanism in order to give the 10-member intermediate, which I showed on previous slide, and finally it undergoes a hydrolysis. So with this, we are able to get the extensive substrate scope for this reaction. Not only the two alkyl furans, but two aryl furans also work well. But you can see on the right side, instead of the mesh acridinium catalyst, now we use the riboflavin kind of photocatalyst, because each photocatalyst and the amount of energy or excitation of the wavelength is differ for different catalysts and substrate. So for that reason, two aryl furans which needed some other catalyst, for that reason we have used the riboflavin. Also, we could able to establish a nice substrate scope for this transformation. Here, the second portion was the photohydrolysis of furfural. Previously, with the furan, we could able to do the hydrolysis and open up the ring. But in this case, surprisingly, what we able to see, we got some rearrangement of these two substituted furans, and we could able to get trans dihydroxy compound. At the bottom portion, you can see. At the bottom portion, you can see there are some natural products which called the pentenomycin 1 and pentenomycin 3, which can be obtained in a single step starting from the two substituted furfural derivative. Till now, everything was fine and it was working well. With our colleague, we could able to establish this reaction in batch. The reaction was working only in NMR tube. Till now, whatever the studies was done in NMR tube. The scale of the reaction was very small, 0.12 millimole scale. The moment we go from the NMR tube to some vial or round bottom flask, we could observe the reduced yield or very poor yield when we use some other glasswares to perform the reaction. So what could be the reason for that? The reason lies between the Beer-Lambert's law, where we can see the attenuation effect, or we call simply light intensity decreases when we increase the distance of the reaction mixture or reactants in the flask. So in batch, what happens actually when we irradiate the light? Most of the light is only gets strike on the wall of the round bottom flask or vial. That's why most of the starting material is not get irradiated. So how we can solve such type of problem? What we can do, we can take a smaller reactor. Smaller reactor means what? Now we have to think some unconventional type of reactor here. So for that reason, we went. For that reason, I have used my expertise in the flow chemistry, and we model some 3D printed reactor, and we use the commercially available pieces in order to customize our photoreactor. So to enable to establish the new reactor, first we need to consider, or we need to understand how the chemical reaction works and what are the different parameters are required for a completion of a successful reaction. First parameter is temperature. Then we have the mixing, which is one of the key component in normal batch chemistry, where we use these stir bars or magnetic stir bars to perform the mixing. But there are other ways to perform the mixing in a tube reactor that I will discuss now. Another aspect of the successful reaction is concentration as well as surface to volume ratio. So this parameter is very crucial, because once you want to go from the small scale to large scale, the surface to volume ratio plays very critical role. Let's take an example of our human body. If you see, all the blood vessels in our body are like very lengthy in nature, and it's spiral around our whole body. Imagine that if we don't have vessels in our body, we don't have these blood vessels in our body, and simply there is one pot and all the blood are inside. So that's not going to give us a better surface to volume ratio. So for that reason, if we think of doing this to get the higher surface to volume ratio, we have to minimize our reactor volume to very small extent. So if you see the conventionally, the reaction used to be done in very big open earthen pots, which is centuries old. Then there was some advancement in science, and then what happened? We get the round bottom flask in early 1600s, which had some weird shape. Then it went to improvements later in the 18th and 19th century. We able to use the simple round bottom flask to perform reaction. So here you can see the big pots now, they got smaller in nature. How about we go little bit more smaller? What about some micro channels or some compact reactors? The size of those reactors will be like kind of palm of our hand. So is it possible to do such kind of reactor modeling or chemical engineering? The answer is yes. There are already methods which uses such kind of reactors to perform chemistry. So just to distinguish, this is simple batch reaction. We have round bottom flask, we add reactants, we stir it using a magnetic stir bar, and we get our product. However, in flow chemistry, what we do, we use the continuous mode of two reactants. We use some sort of pumps. The pump, what it will do, it will deliver the reactants and it will get mixed in some mixing piece. And due to the very narrow small size of our tube, it will give a better mixing. This will also improve the mass transfer ratio as well as temperature, and it will drastically change the outcome of our reaction. So this reaction are performed on a continuous scale, and the product can be finally obtained or isolated by using simple downstream processing. So with this, I have shown this image. You can see this is a simple tubular reactor. Inside that, we have a PFA tube. PFA tube is a polyfluoroalkoxy tube, which is used to deliver the reactants, and it get reacted in a temperature control manner. So, now you can see. So if we use such type of small tubings, what it will do, it will give us opportunity to irradiate light very nicely onto these small tubes. So with this principle, I would also like to introduce you with some terminologies of the continuous flow equipment, or a schematic of the flow equipment. Here you can see on the left side, there are pumps which deliver the reagent. Then we have the core portion, which is called a reactor. So the reactor can be of different size, which will be a chip-like reactor, which will be a kind of a very narrow tubes, which will have the grooves carved in that reactor, and it will allow two reactants to mix. Then there are simple coil reactor, which I've shown in previous slide the photograph of that. And there will be a packed bed reactor when we can use the heterogeneous catalyst as well as the polymer supported immobilized catalyst onto that packed bed. There will be a second portion which called quenching. So if we introduce some other pump and quenching reagent, we could able to quench our reaction mixtures. Also, in order to just to regulate the pressure, if we use some kind of wall, what it will do, it will regulate the pressure. So imagine your starting material or your reactant, which will have very low boiling point. Or imagine DCM has a boiling point of 38 or 39. And if you want to heat the DCM at 80 degrees Celsius, so is it possible? Because what it will do, everything will get evaporated. But if we use some kind of pressure regulator, if we pressurize the system, what it will do, the vapors of the DCM will be in condensed form and which will remain in the liquid form. So this is one of the beautiful function of the flow process we can think of. Also, there will be some other optional things which will be inline analysis. Here, what we'll do, the continuous stream of our reaction mixture, we can integrate with some analytical tools such as inline IR or inline NMR. So we no need to isolate the compound, take it out, then do characterization. So instead of that, we can also think of using inline analysis. So these are some terminology which I will use in my talk, which if you are familiar, then it will be easy to understand. So residence time, which is one of the terminology, it is nothing but a time spent by the reactant inside the reactor. Productivity is nothing but amount of product produced per unit of substrate consumed in hours or minute. And then the BPR, which is a back pressure regulator, which will be used to regulate the pressure and smoothing of our reaction. So with this now, I will move to the main project and I will highlight some of the existing designs which were already in the market. If you can see this type of photo flow reactors were already available in market, but the problem is if you see there is a poor light contact with the reactor and most of the light is get wasted. Also, the another problem is there is no temperature control, and if you think of buying a commercial this photo flow reactor which costs around 12,000 pounds, and it will the limitation of those things also, it will be having only a fixed reactor, so we cannot change those reactor volume. If you want to do small scale reaction, let's say at a milligram scale, then we cannot do that on the commercial one. Then that's why we thought to customize our inbuilt homemade photo flow reactor. So for that reason, what we did, we took the help of glass blowers and the fine mechanics team in order to do the 3D printing. Here you can see this is the cylindrical glass, which is spiraled by the PFA tubing, and there are two ends. One is to introduce the reactant and one end is to take out the product. Another component is 3D printed. This provides a support for keeping the cylindrical glass. You can see in the third picture, inside another cylindrical glass, we have placed the LED stripe. These stripes are easily available in market, and most of the people now they use the LED stripe to decorate their home as well as car or bedroom wardrobes. So this is we thought to utilize such LED stripes for doing chemistry for our purpose. So now we put this LED stripe inside and we place the first cylindrical spiral tube cylindrical glass inside the reactor. Also, we have 3D printed some grooves to keep the compact fan on the top of that, which will cool down the reaction. And this is the final customized photo reactor. So what it will do, if you see, it is circular in nature. Inside that, we will have this centrosymmetric irradiation, and it will be very intense in order to drive our photo hydrolysis of furan. So this is the actual setup it looks like. Oops. Yeah, so here we have used the, you can see in the purple color, it's SF10 pump, which delivers the reaction mixture. Here reaction mixture contains the furan, acetonitrile, and photocatalyst. And on the right side, you can see this small black box, which is our photoreactor. So with this, we went ahead for the optimization of photo hydrolysis of 2-methylfuran using continuous flow. So we have performed the solvent studies because this reaction was very sensitive to the ratio of acetonitrile and water, because water itself is one of the reactant in this reaction. So some more condition we have tried to optimize, such as flow rate, light intensity, and type of tubing material. So instead of PFA tubing, if you use some FEP tubing, what it will give the outcome? The outcome was similar, but if you compare the cost of these two material, these two tubing material, the PFA tubing was slightly cheap in nature. So that's why we went ahead with the PFA tubing. So here now you can see on the arrow, we have the 10 ml coil reactor, and we irradiated it with 450 nanometer of blue LED. Temperature of the inside reactor core was around 70 degrees Celsius, and flow rate was 0.15 ml. So if we calculate the overall reaction time for this reaction in flow, it was around 67 minutes. Now, if we compare this into the normal batch reaction, which we carried out in NMR tubes, which was 24 hours. So we get a drastic improvement in the time of this reaction. Also, initially we thought the reaction of furan will be more challenging because of its polymerizable nature, but it turned out to be not the case. We got a better result as well as the output for with the furan derivatives. Here again we have optimized this reaction, and by changing the flow rate of the reaction or reactants, we could able to tune the productivity, and we established some of the reaction metrics that I will show now. In order to show the safety of the reaction, we perform this reaction continuously for 1000 minutes, and we monitor the reaction progress by NMR spectroscopy every 100 minutes. And then when there was a night time, we skip some samples. Then we get around 350 minutes, then around 800 minutes and 1000 minutes. You can see the consistent conversion, which ranges from 99 to 100%. For 2-methylfuran, same thing we did. We did long time experiment, and we could able to establish this. We could establish this multi-gram production of photohydrolyzed product. So in order to do the scale up, what we did, instead of now one simple reactor, we combined three reactors, three photoflow reactors, each consisting of 10 ml reactor volume, and these are the productivity metrics. So for 2-methylfuran, we could able to produce 31 millimole of product in one day, which correspond to 0.31 kilogram dm cube of space-time yield. For furan, with 30 ml reactor volume, we could able to produce 252 millimole of product in one day. And if you want to do scale up of this reaction, we just simply need to use the bigger reactor and what are the starting materials available in large quantities. So with this, the application of the succinaldehyde can be found in variety of compounds. One of the major starting material, which is called alpha beta unsaturated cyclopentanone, which is a precursor for hedione. So hedione is a very valuable compound, which is which can be found in varieties of perfumes and fragrances. If you see the brand called Valentino perfume name, so it contains this hedione in very small amount. So the threshold of this hedione compound is very high. So even it can last up to 40 hours once you apply the perfume on your body. So also there are some other alkaloids that you can see on the right side. There is a tropinone. The tropinone is a precursor for atropine. In World War, there was like the soldier used to get injured, and and also they need some anesthesia or such type of neurodegenerative drugs. For that reason, during World War, the Robinson, he came up with the synthesis of tropinone, and for that reason, we can use the succinaldehyde as a starting material. Also, if you see on the bottom side, there is the starting material for prostaglandin, which was developed by Agarwal. So with this now, so I will show the telescoping in flow. What does mean of what does it mean for the telescoping? Telescoping is nothing but without isolation of any reaction, we can do the second reaction. So in order to establish that, we try to optimize two steps separately, and then we thought to combine that in one single step. So you can see at the bottom, we could able to do the photohydrolysis, and directly we connect the next starting material, which is methylamine and 3-oxoglutaric acid, and we could able to get the tropinone in not great, but less than 10% yield. So this process still need to be optimized in order to get the improved result. So in summary, we could able to establish a photohydrolysis process, and we could able to also design one photoflow reactor. This reactor was the reactor was very simple to make, and the process was very robust. So this work is recently published in Science Journal. I usually don't talk about the impact factor, but I think this is the best we can get in organic chemistry. So with this now, I will just move to my second topic. This is slightly different from this previous work. Here, what we did the peroxidation of carbonyl compounds to get novel anti-cancer as well as anti-malarial scaffolds. So if we see the statistics in 2022, the global cancer data says 19 million new cases and around 10 million deaths due to cancer. In 2024, the global malaria data suggests 282 million cases with 610,000 deaths. Most of these deaths and these cases, they are very common in African countries, where those countries are very poor and they don't get the proper medication. So also you can see on this graph, in Asia, we almost constitute around 48% for the cancer cases. So what could be the main reason? Although there are several medicines in the market, but the increased resistance against the medicine make them effective, which inspire a chemist like us in order to do some new drug development and new drug discovery. So taking this inspiration, we digged out literature and we thought how the cancer cells can be targeted. So there are several ways to target the cancer cells, but one of the important one and in which we were interested was ferroptosis. The word ferrop does means the iron. Tosis means the death. So this literally called the iron-induced cell death of cancer cell. How does it work? Due to the presence of iron in the damaged cells, it undergoes an overload of iron and presence of reactive oxygen species such as peroxides, which triggers the cell death of the cancerous cell. So we have iron present in our body in the form of hemoglobin, which is responsible to undergo a fentone type reaction with peroxide. So now you can see this very complex molecule on the top. So, and this is the complete cycle of ferroptosis in cancer cell. So in the structure, you can see there are two oxygens present. This type of functional group called peroxide. The properties of peroxides are very unique, and it has the bond strength of 150 to 190 kilojoule. These are common peroxylating reagent can be used to perform the chemistry of peroxide. But there is one problem. If we heard the word peroxide, they are explosive in nature. When they react with each other or any substrate, it generates a lot of exotherm, and they are heat as well as shock sensitive. So how we can handle peroxides on large scale, or if you want to do some reactions out of that. So these things I will discuss in my next slides. Although they are dangerous, but the peroxides are very versatile functional group and can be found in several natural products as well as drug. So you can see on the first example, this example is very unique and important. You can see the artemisinin, which contains this complex molecule, which constitute more than 6 stereoisomers. And you can think about how many isomers it can form if we want to isolate each and everything. So this is called artemisinin, which shows the anti-cancer as well as, first it shows anti-malarial activity, and it also shows anti-cancer activity. In the end, I will be able to convince you all the anti-cancer compounds are anti-malarial, and all the anti-malarial compounds are anti-cancer, depending upon the mode of targeting the cancerous cells or unhealthy cells. So for the discovery of artemisinin, the UU2 was awarded with the Nobel Prize. While coming to this college, we were discussing about this chemistry. And in China, what they used to do, if someone get the malaria, they just take the plant, this plant called Artemisia annua. They take this plant, crush it, and give to the patient, and then magically the malaria will go away. So the UU2 was the researcher. What she did, she spent her life in order to elucidate the structure of this compound. And for her contribution to elucidate the structure, she was awarded with the Nobel Prize for her discovery and elucidation of this compound. And this compound now, so this compound was widely used in treatment, and it's commercially available. And there are many companies, IPCA, then some pharma related company, they do the commercialization. So just to go forward now, you can see these very beautiful complex structures. And in order to synthesize them, chemists need to come up with very sophisticated synthesis. And it takes almost 5 to 12 steps for the synthesis. So it makes our life difficult in our, like the PhD students or postdocs or MSc student, difficult in order to get this 12-step synthesis. So this inspired us. How about we develop some molecule which will be very simple to make, which can be maybe synthesized in one step. So for that, we have chosen some of the molecule called the family of oxyindole, barbiturate acid, coumarin, as well as tetralone. Although tetralone don't have many biological application, but these initial three ones, they have excellent biological properties. If we have a particularly pharmacophore on those moiety, and why they are good, because the metabolism of these compounds can be easily excreted from our human body at the end. So our hypothesis was, let's use the earth abundant metal, which is iron, so which will trigger a Fenton type chemistry, which will generate some radicals, and it will go undergo some oxidation and reduction kind of reaction. So we have chosen these three substituted to oxyindole in order to do the optimization. And initially we have started reactions without control experiment, without using any catalyst. It didn't give any reaction, and then we screen our next conditions, and we could able to see with iron 2 or 3 reaction work well in presence of some nitrogen containing ligand. So we established a substrate scope for this transformation, ranging from electron donating, withdrawing, and several other things. Not only 2-oxyindole, but barbituric acid as well as coumarins also work well in this transformation. Then later, everything was fine, but the problem was once you mix the reactant such as peroxide and metal with each other, it will generate high exotherms, and reaction undergo in uncontrolled way. It will heat up our round bottom flask or any reactor vessel what we are using. So for that reason, we have used the approach of flow chemistry now, because in flow at a single time we are only passing very small amount of reactants. That's why what it will do, it will lower down the exotherm. Instead of round bottom flask, we directly add some of the things. But some of you may argue, in round bottom flask we can add very simply, like slow addition, but it's again time consuming and handling such reactive species which is not feasible sometimes. So that's why the approach of flow chemistry can be rational in this case. So we could establish some nice parameters as well as substrate scope for these peroxides. And as we anticipated initially, so peroxides, they will undergo some sort of ferroptosis reaction in cancer cells. So for that reason, we have collaborated with the chemical biology team at ICFCMS Pune, and these are the biological evaluation for some of the compounds. Here we got 3 best compounds with IC50 value ranging from 5 to 13 micromolar. And at the bottom, we have shown the control already available drugs in the market. So although we got some good things with some of the compound, but there are still the the efficiency or efficacy of the drugs still need to be high. So these are some mechanistic aspects. We started with the establishing the nature of the reaction. Does it go via radical mechanism or ionic mechanism? So for that reason, we use some quenching radical quenchers such as tempo, 1,1-diphenylethylene or alpha-methylstyrene. Also, the molecular oxygen, it is also one of the radical quencher we can use to prove the reaction. In presence of these quenchers, we could able to see the drop in yield of the reaction. This suggests that there is involvement of subradical. To give the concrete evidence for this, we have performed the EPR, electron paramagnetic resonance studies, and we could able to see the signals for organic radical in EPR spectra. Also, based on that, we could able to establish some plausible reaction mechanism for this, and I'm not going to discuss it in very detail. If you are more interested, you can follow our paper on this work which is published in JOC. So everything was fine till now. We were using homogeneous catalysts, but the problem with the homogeneous catalyst sometimes is we cannot recover and reuse them for the next reaction. So for that reason, we thought, okay, let's use some heterogeneous catalyst which will be reusable after each reaction. This way, we can reuse and recycle this catalyst, and we can improve the sustainability of the process. What we did, we digged out some literature, and what we found that we can use earth abundant iron source, and by co-precipitation technique, we could able to get the iron oxide nanoparticles, which are magnetic in nature. In the end, we just do the simple magnetic decantation, and the solvent or reaction mixture can be separated. So it was characterized by using all available techniques such as high resolution TEM. Then we had a simple TEM to get the structural morphology as well as average particle size. We also perform the same analysis in order to get the cluster formation we could able to see in this image. Then reviewer asked us, okay, this all a technique that doesn't show the presence of oxidation state of iron in your material. So for that reason, we have performed this XPS analysis, which actually a surface phenomena which irradiate the X-ray photoelectron beams on our heterogeneous catalyst, and which give some sort of information which can be correlated with the iron 2 or iron 3 species. And you can see on the left side, we found that the presence of iron 3 species. So with this now, we again went for substrate scope in batch, and we could able to show the recyclability of the catalyst. Everything was fine. The catalyst can be recycled up to 10 runs. Only the problem was this looks after reaction is very ugly, and so most of the time these heterogeneous catalysts get stuck on the wall of the vials. So what we can do, can we use the approach of packed bed reactor now, where we can simply take our catalyst, place inside a cylindrical packed bed, and we pass the two reactants. So you can see in this picture, the nanoparticle floating in this packed bed reactor, and we could able to flow the starting material, catalyst, and reactor using single pump. So in the end, we could establish this protocol. You can see now the time is only 7.9 minutes as compared to 24 hours, 4 hours in batch. This also gives us a rapid reaction improvement. And such type of reaction discovery can be very useful if you want to synthesize a library of several compounds. Then we showed long-term studies up to 40 hours, which show periodic drop, which is one of the limitation of this work. And finally, by looking at this structure of this compound, they contain the peroxide moiety. We thought, can we use them as anti-malarial compounds? And we collaborated with a biological team at ICFCMS again, and there were a few good hit in this library of this compound. And you can see the two entries which shows 2.93 micromolar IC50 values for antimalarial cell, which is Plasmodium vivax. So there are some control drugs which are already available in market. Our newly synthesized peroxy compound, it shows a little bit comparable results to that. So in the summary, we could able to establish a flow process for a CH peroxidation in a safer and on-demand manner. We could able to do it on a homogeneous as well as heterogeneous manner. Finally, this is me with the Professor Benjamin List holding his Nobel Prize. And the weight of this Nobel Prize was 166 gram of gold. So, and then finally, I would like to thank all the organizing committee members and giving me opportunity, especially to Professor Rahul sir for inviting me, as well as all the faculty members and whoever involved organizing such a great conference. And thank you all for your kind attention. And last but not the least, the financial and research supports which I got from various funding agencies such as Marie Curie, which using that I could able to do the research at Spain. Then we had University of Liverpool, Max Planck Society, ICIQ, ICER Pune. And this picture was recently highlighted for our science work in C&E, chemical and engineering, as well as some other social media platforms also. And thank you so much for your kind attention. And if there is any question, I'm happy to take.
So thanking you, Dr. Murishar Chaudhary, the researcher who gives the best in so one of the best researcher in the worldwide. His profile, I would like to say that it is more compatible, and the topic from his given the lecture from this international conference, from batch to flow, intensifying chemical transformations. And now the session is open for the discussions. If you have any queries, any question in your mind, you can ask the Dr. Murishwar Chaudhary from the participant sides, faculty, as well as the researcher. Those participants are also joining in online. He or she also asks the questions by drop the message on chat box.
I think there is no question in chat. From the audience? Yes?
Yes, sir.
Yes. Dr. Sisa.
In terms of this chemistry, like hydrolyzing the furan is not feasible by means of the metal catalyst or other organic catalyst. This need actually the light as a source and some sort of oxidation potential, which is like around 2.7 electron volt. If we able to do that, if we able to achieve that electron volt of potential, then we may able to break the furan. But again, the problem is once you do the hydrolysis of furan, the aldehyde, what we get, which is not stable. So we need to keep in that mind what kind of catalyst we are going to use, which should not interfere with the product. So in terms of immobilization, so there are some ways where we can immobilize the photocatalyst also. So instead of going to the metal and simple catalyst, we can think of immobilizing the photocatalyst. That way we may able to achieve. But again, you need to consider the transparency of the immobilized material what we use, because let's say we have this material and the light should penetrate from that immobilized material. So there are some certain factors, but it's really nice idea. If you want to pursue that, it can be feasible.
Okay, sir. Sir, one of the question from online.
The reaction kinetics required for the reaction to increase. Yeah. The reaction kinetics, the reaction to
So basically, it's based on trial and error. So if we want more data points, then we can think of doing the reaction kinetics. But it's just a matter of what we want. Actually, in our case, we did the reaction kinetics just to prove that the reaction is safer. Because once you have some light intensity, what it will do after certain time, sorry. So after a certain time, which will create a large amount of heat. So to prove that our reaction is safer, we did the reaction reaction kinetics.
Where is my question?
Any question from audience? I think no questions from the audience. Now move towards the. Okay, so Dr. Morishwar Chaudhary sir is briefly highlight why the batch to flow transformations in timely and transformative topics in a chemical science and engineering, and he emphasizes global drivers from the global worlds. Sir, cover in his topic the immobilization of organic catalyst, photo flow hydrolysis, fossil fuel versus the bio-based compounds, polymer industry, oxidative process, furan and fluorides, photohydrolysis of furans with the flow chemistry, and he developed a reactor in which the batch reactions to the flow chemistry. This is the beauty of these reactions. Already sir has emphasized all these reactions and prepare their derivatives of furans. Sir also cover the customize the assembly for the photoflow reactor, their optimization for photolysis of 2-methylfuran and its derivative by using the continuous flow and its applications. These applications in the medicinal field as well as in the fragrance also cover the telescoping in flow, that is propylene to the telescoping process. Sir, cover the targeting cancer cells and focuses on the peroxy group, which is the pharmacophores like, and it's overlooked with the some scaffolds, which is used as the globally market as the antimalarial drugs. Their conceptualizations of catalyst role in the flow chemistry for safer, scalable and the reactions development times. The role play the heterogeneous catalyst for the peroxidations reactions and their characterizations. He already said that. He covered the characterizations like the XPS, same time, etc. Sir, you have to give a lot of things in this photoreactor as well as the flow photochemistry and preparation of its derivatives. So some questions from my side. Sir, what are the parameters to set the temperature, pressures, and other parameters? If the photoreactor, you have to scale the reactions, and that gives the better yield. I think you have to show that the yield is minimizes. So how to overcome this yield with some parameters you have to change, or any change or modification in the photoreactor?
So the question is what kind of parameters we can tune up to get the better selectivity or yield. So for that reason, I think if the reaction needs cooling, then we can think of using external circulating liquid which can cool down the reaction and which may give better yield, because during heat, a large amount of exotherm or heat, what it will do, it will decomposes our product. That way also we can lose some of the yield. So in terms of pressure, so if we are using some of the starting material which has low boiling point and we are hitting above to its boiling point, in that case we need to use the pressure regulator, as well as to avoid the slug formation or any gaps in the photoreactor or flow reactor. In that case, we need to use the pressure regulator. So when there is such parameters involved, that case we need to pressurize the system, and by tuning the different pressure values ranging from 20, 40 or 70 psi, we can tune up the reaction outcome. I hope I may be able to answer your question.
So thank you, Dr. Morishwar Chaudhary, sir. I would like to thanks to giving this opportunity to mine for chairing these sessions. Principal, vice principal, and the organizing committee members of this international conference being organized by MSG College, Malegaon. One highlighted point is here, Dr. Morishwar Chaudhary, sir, not just say that, but his paper in highly reputed journals, Science, Chemcom, as well as, I think, JOC, say one of the best researchers whose profile say lots of. So thank you, sir, being with us. Thank you.
Very well, gentlemen. We sincerely thank our listeners for sharing this valuable knowledge with us. We also extend our heartfelt thanks to our session chair, Dr. Santosh Patel, for expert sharing this session. With this, we formally conclude. Thank you all for participation. Now we are moving to the next session. For this, we have Dr. Nicholas Zenda from Switzerland. I request Dr. Sandeep Nair sir to introduce our Indian speaker, Dr. Nicholas Zenda.
Thank you, Shinde sir. It is a great pleasure to introduce our distinguished speaker for the second session, Dr. Nicholas Zenda sir. Zenda sir is a chemist with over 8 years of experience spanning academic research and industrial drug discovery. He holds a degree in chemistry and pharmaceutical technology from University of Cagliari, Italy, and has received international academic training through the Erasmus Plus program. He further specialized in medicinal chemistry at the Autonomous University of Madrid. He completed his PhD in chemistry at the Institute of Chemical Research of Catalonia, Spain, as a Marie Curie and La Cassia Fellow under the supervision of Professor Michael A. Faricas and Arjun W. Clegg. His doctoral research focused on carbon dioxide valorization using immobilized catalyst in batch and continuous flow system, resulting in peer-reviewed publications. During this time, he also served as a laboratory safety coordinator and undertook a research visit to Graz, Austria, working on electrochemical reactions. Currently, Mr. Zenda is working as a research chemist second and project leader at Spirochem Basel, Switzerland. We are pleased to have Dr. Nicola Zenda with us today and look forward to his talk on continuous flow catalysis for valorization of carbon dioxide. Over to you, sir.
Okay, sir. For this session, we have a session chair, Dr. Ashwin Kajri, sir. I request Dr. Ashwin Kajri, sir, from the line. Let me introduce Dr. Ashwin Kajri, sir. Ashwin Kajri, sir, working as an associate professor at NTU's ACS College, Manipur. He published many research articles in many reputed international journals, also published paper. His research area is synthetic organic chemistry, also from chemistry, sir, on behalf of organic committee, I request you to share this session. Now, this session is over. Thank you. Dr. Nicola Zenda, you can start.
Good morning, everyone. So I didn't get the last part. I think there was some disturbance in the audio, but thanks for the nice introduction. It's a pleasure for me to be here and share my research. As I was introduced, I will be talking about the continuous flow catalysis for the valorization of carbon dioxide. So, as I was also introduced, this was my path, but I would still like to say some words about me. What passionates me is to use technology to boost and improve the drug discovery and the organic chemistry in general. This type of approach for me was introduced and was very relevant from that moment on, since I joined Janssen in Toledo. We were using flow chemistry to actually boost the drug discovery process. I continued this in the ICQ during my PhD, where I worked in continuous flow applications for supported organocatalysts, but also for some supported metal catalysts. And in general, I focused on triphasic reaction, so gas, liquid, solid type reaction. At the moment, I'm based in Switzerland. When I'm, as I was introduced, research chemist and project leader. And here I deal with medicinal chemistry, raw scouting, and highly potent molecules. And plus, I'm the responsible for the development of flow chemistry in the company. So today we will be focusing on my experience in Spain on the triphasic type of reactions. This is the general structure of the presentation. And actually, the core of it focused on the valorization of CO2 to make relevant molecules. But since we recently published a paper about asymmetric hydrogenation, and since it's still in the topic, because it's relevant from the flow chemistry point of view, then I would like to also talk about this by the end of the topic. But first, let's start with a brief introduction about why we want to use CO2 and why this is so important. So in many talks, it's said that we want to use CO2 as a synthetic reagent to actually reduce the pollution. This is actually not completely true because all the combined synthesis could not actually reduce the pollution by using the CO2, and plus CO2 will be released afterwards in the environment. But what is true is that since many techniques of carbon capture and carbon storage were developed during the years to tackle this problem of the pollution, then CO2 became abundant and readily available reagents in every laboratory. Furthermore, it presents advantages in comparison with other C1 symptoms such as phosgene, because it's not toxic being a gaseous reagent, is also highly recyclable. There are some problems involved in its use, because since it's a highly thermodynamically stable molecule, then you need either highly energetic reactive. Sorry?
ब्रेक 12:30 ते एक ब्रेक होता हाँ हाँ
Sorry?
Yes, sir. Speak.
Okay. I heard some voices. I thought I had to stop. Okay. So to actually use it in synthetic chemistry, you need either highly energetic partners, such as epoxide or Grignard reagents or organolithium reagents, or energy demanding conditions, so high pressure and high temperature. In this scheme, so there are summarized the main uses of CO2. So you can have the reduction of CO2 either by methylation of amine or formulation of amine, or you can have partial to complete reduction into energy vectors, such as methanol, formic acid, or methane. Plus, you have a broad class of reactions, which is the carboxylations, in which you can carboxylate alkynes and alkenes, or also aliphatic chains.
इंटरनेशनल कॉन्फ्रेंस है
From an
मालेगावला.
industrial point of view,
हे बघा निकोला झंडा त्याचं लेक्चर चालू आहे.
from an industrial point of view, this reaction here, as was depicted, is very important because it is the synthesis of salicylic acid, so aspirin, and this is actually performed from sodium phenolate and carbon dioxide. And then there is another class of reaction and compounds that are relevant from an industrial point of view, which are the functionalization of CO2 into carbonates and ureas, and this can be both cyclic or linear. And in the first part of this talk, we will actually focus on cyclic organic carbonates and carbamates, and then we will switch towards the formulation reaction. In our groups, what we tried to do was to apply heterogeneous organocatalysis to the carbonate formation. To do this, in the years 2014 and 2017, we developed some dual catalysts, which used hydrogen bonding features that you can see here and here, and halogen catalysis to be able to activate the epoxides and then run the reaction. Although these catalysts were robust and presented at broad scope, there was the limitation of leaching of the halogen co-catalyst into the reaction stream. And since what we wanted to do at the end was to have a possible in future industrial process, we wanted to avoid the halogen waste stream because this is actually treated as a special type of waste and is more expensive to deal with it. So in our work, we wanted to focus on purely base catalysts without any co-catalyst that could leach into the reaction stream. As I mentioned, we wanted to work at the end in continuous flow. But why was that? So actually, thanks to the nice talk of Dr. Moreshwar Chaudhary, so I won't need to explain many parameters about flow chemistry, but I will focus on why flow chemistry is important in high pressure reaction. So when you want to run this reaction in batch on laboratory scale, you can think of having an autoclave, and then you will have to load your catalyst and your sample, then close the autoclave, pressurize it, and run increase the temperature. Run the reaction, and when the reaction will be done, then you will need to cool it down, depressurize, and then do the workup or purify the compounds, because you will need to separate them from the catalyst. So these actually, there are many operations, and it could be tedious to perform. Plus, there is always, since this is a pressurized reactor and under extreme conditions, there is always the question if this is safe to scale up. Of course, there are safe reactors in batch, but these are highly specialized reactors, and you probably they will be also expensive. A possible alternative, at least from the operation side, was to use the heterogeneous organocatalyst, and that's why we actually started developing them. And in this case, all the separation steps won't be performed, because just by filtration of the reaction crude after the reaction time, the product will be obtained cleaned or nearly clean. But of course, also in this case is a batch pressurized vessel, which has a large volume to be heated and to be pressurized, and this poses questions about the safety. Instead, there is the alternative to use an heterogeneous flow mode. And in this case, the heterogeneous catalyst will be placed in a column type reactor with filters on the top or the bottom to avoid its movements. And then the operation will be as easy as pressing one button to flow the feed of starting material with gaseous reagent into the catalytic bed, and then collect the product at the end. Furthermore, since these reactors are smaller in comparison with batch reactor, there is less volume to be heated and put under pressure, and this increases the safety of the operation. So I hope by the end of this talk, I'll show you how we can integrate organocatalysis with the CO2 valorization in a continuous flow, and that we could develop efficient organocatalyst that could actually avoid the halon-based additives. And then I'll show you some interesting molecules that we prepared. So at the beginning of our work, we decided to start with glycerol carbonates and starting material glycidol. Because, well, first of all, there were no examples in mild conditions that employed heterogeneous organocatalysts with a pure base center, and that were not using an Hale co-catalyst. And another important reason is that glycerol carbonate is one of the few carbonates that actually has a commercial relevance. In fact, this is found in many industries. And to name a few, for example, is found in cosmetics as a formulation agent in perfumes, but is also found in pharmaceutical formulations. It's used in polymer chemistry, and is an additive in construction in the cement formulation. And our goals on this work were to have a supported organocatalyst without any metal or halide that could work in mild conditions, and then that could afford a stable and multigram synthesis. To do this, what we did was to design a library of catalysts with an easy design that could allow us a certain degree of variability. So we had 3 points of diversification. In fact, we could diversify from the base point of view. So we tested TBD, we tested pyridine and DBU. We wanted to vary the linker, which is important to anchor the catalyst to the support. In this case, what we wanted to test was the possible effect of the neighboring hydrogen donor hydroxy group, as you can see in this catalyst, or its absence, as you can see here in catalyst number 4. Finally, the third point of diversification was the support. In fact, the support is often overlooked, but it actually has a huge impact on the reaction and on the kinetic of the reaction. Mostly in our design, we wanted to focus on swellable supports. And for swellable, we mean that this can actually form a gel phase once put in solution. And this allows the catalyst to have properties in between homogeneous and heterogeneous catalysis. So it still has they still have the advantages of heterogeneous catalysis because you can actually easily separate them from the reaction. But they show behavior as homogeneous catalysts. And in this case, I'm referring especially to the mass transfer, which is not that concerning in the case of this type of catalyst in comparison with the heterogeneous catalysts such as or supports such as mesoporous silica. So here is a scheme that summarizes the main results. The screen of the catalyst was performed first in a batch. And to do this, we employ the Amtech SPR16 reactor. And this allows us to run up to 16 reactions in parallel under pressure, and with the possibility to vary some parameters at the same time, such as pressure, temperature, but also the isobaric or not condition of CO2. So we had the possibility either to charge the CO2 at the beginning of the experiment and then follow the reduced pressure while the CO2 was consumed, or we could apply an isobaric condition of CO2 and then follow the gas uptake of CO2. And this we'll also talk in the following slides. In terms of catalyst, the best one was the TBD supported or Merrifield here that afforded almost homogeneous-like conditions that you can see here with the methyl TBD. While there was one was the polyvinyl supported pyridine, which presented actually low yields and a high degree of hydrolysis into glycerol. In terms of concentration, these reactions are known to perform the best NEAT, but also methyl ketone was a good solvent for them. And then regarding the temperature, we actually observed that the optimal temperature was 70 degrees, because with this temperature, we could achieve high conversion and low degree of hydrolysis, while increasing the temperature to 80 degrees, the hydrolysis became an issue. So we observe an increased amount of glycerol. And instead, when lower temperatures were employed, it's true that we didn't have hydrolysis, but we also observed lower conversion. In terms of the catalyst, many behave actually in a similar fashion, but the TBD supported on Merrifield and the DPU and the TBD supported on silica appeared apparently similar. As you can see here, the yields were in a similar range, at least at the beginning of our experiments. And what made us choose for the TBD supported catalyst rather than the on Merrifield resin, rather on the mesoporous silica, were actually the gas uptake graphs. So these were taken actually from different experiments, but and we use them more in a qualitative way rather than in a quantitative fashion. But as you can see here, both the graph of the TBD supported on Merrifield and the DBU supported on polystyrene presented a really steep consumption of the CO2 at the beginning of the reaction. And then once the reaction was reaching the nearly quantitative conversion, then it was stopping. And this was expressed in terms of milliliter per hour that were used. Instead, the TBD supported of mesoporous silica, even though at the end was achieving similar conversions in most of the experiments, then it has slower kinetic. And since we wanted to transfer this reaction in flow, we were more interested in a faster reaction that could intensify the process in an easier way. So with the catalyst on end, we decided to design the setup for our flow chemistry application. And of course, we had to keep in mind that our catalyst was a swellable one. So to be used in the proper way and have all the catalytic sites exposed, then needed to be in a gel phase. To do this, we design a setup that employs CO2 completely dissolved in the stream, and that allows to have in this case, a biphasic system during the reaction, so just liquid solid. To do this, we employed a tube-in-tube reactor that you can see here in the picture on the right. And this is made out of one inner tube and one external tube. The inner tube is made out of a permeable polymer, which is selective for gases and doesn't let the liquids pass through. And thanks to this, we could saturate the stream of starting material that was passing through, and then pass it through our preheating coil, and then the packed bed that here in the picture is hidden here below all the isolating material. Since we loaded the CO2 at room temperature, and we were heating up the reaction at high temperature, and according to Herrera law, the solubility of the gas actually decreases by increasing the temperature. Then we had to apply pressure of the system through a back pressure regulator, which is placed at the end of the system, and that here is here at the top. And thanks to this, we could actually achieve an homogeneous reaction stream that could allow us to run the reaction. After many experiments of optimization, we achieved a high conversion we using half an hour residence time. So you can see experiment 14 and 15, which were our best case. And actually the condition of 14 with this catalyst loading were used to run the stability test in terms of recyclability of the catalyst with partial cycle. And instead this final run was our scale up, which was performed in 2 days of operation. And to achieve higher conversion, we simply increase the catalyst loading. So overall, the same parameter that affected the reaction in batch were affecting it in flow. So of course, higher pressure of gas in the tube-in-tube was allowing to have increased amount of CO2, thus improving the kinetic of the reaction. Methyl ketone was still performing the best in flow and as like what we saw observed in batch. Then of course, increasing residence time, so the time that the material passes inside the reactor also was beneficial for the reaction. As I said, we used the entry with 90% of conversion to run some stability tests. The stability tests were run in batch, and we basically wanted to see if we could recycle the catalyst over some days of operation. These experiments were run over 2 weeks in total. And the way they worked was that we were flowing the material, reaching the steady state. So the moment at which in every point of the reactor, the same conversion is observed and the system is stable for 4 to 6 hours. And then we were observing the conversion by NMR. What we observed was actually that the conversion was decreasing over time, and it seems that the catalyst was not stable. But now the question was that due to mechanical damage or chemical instability of the catalyst? So for example, leaching or the base was degrading. So we were glad to observe that by NMR, IR, and elemental analysis, the catalyst was actually identical to what we previously observed on a fresh batch. But what we did observe by opening the isolating material and observing the catalyst by visual inspection was that the resin shrunk. So it was not able to occupy anymore the volume that was occupying at the beginning of the reaction. And this probably was hiding some catalytic centers, and thus there was less catalyst available for the reaction to happen. And this was influencing the conversion. And this was probably due to the high pressure that we were employing, so 250 PSI, which was probably collapsing the pores of the resin and thus not allowing the reaction to proceed. To solve this, what we did was simply to decrease the pressure of the back pressure regulators of the system from 250 PSI to 190. And thanks to this, we could run our experiment for 2 days without stop. And we were able to achieve stable conversion at 99%, all over the period. What we also observed was an increased selectivity. So the amount of glycerol that was formed was actually negligible in comparison with the batch experiment. And thanks to this, by the end of this operation, we obtained 17 grams of material, which is roughly 150 millimoles, all over the 2 days. So overall, this was a nice showcase. So we were really happy because our catalyst proved to be stable and proficient in the transformation. However, this type of setup, which actually I'll show you later on in another project, showed lack of flexibility. And what I mean by this is that many parameters were interconnected. So meaning the pressure that need to apply and the temperature that could be used to achieve enough CO2 soluble in the system. And this could actually be a problem when more challenging substrates were going to be used. And this is actually what we wanted to tackle in the next project. In this project, we decided to focus on two substituted oxazolidinones as our target, since there were few synthetic reports that were lacking either the selectivity that was required for this transformation or the reactivity. Thus, they always needed a co-catalyst, either an halogen co-catalyst or a base co-catalyst together with the metal. These molecules were also interesting for us because two substituted oxazolidinones seemed like a privileged structure. So they usually have biological activity and they can be found already in various drugs that are commercially available. The way we wanted to achieve this was by preparing a more robust and versatile organocatalyst that could allow us also to have a more versatile setup. Ideally, we wanted our catalyst to be cheap, readily available in every lab, and if synthetic, to be easy to scale up. And then this was actually, the fourth point was actually limitation of our lab. So we wanted the catalyst to be able to work at a low inlet pressure because our lab was limited to 10 bars of CO2. And this, of course, limited also the final productivity that we observed. So many heterogeneous bases that are cheap and commonly available in the lab were actually discarded because they presented both low catalytic activity and elevated pressure drop in the reactor. So with 10 bars of inlet pressure, we were actually not able to run the reaction. What instead was a good candidate was the TBD supported on polystyrene, but this is different in comparison from the previous version of TBD because this polystyrene presented a higher degree of cross-linking and thus couldn't form a gel phase and could be used as a pure heterogeneous organocatalyst. And this was going to allow us also to use CO2 as a gaseous reagent and thus having a triphasic system, so gas, liquid, and solid. And here is just on the right is a picture of how this catalyst looked under SEM analysis. And here on the left inside is the catalyst inside the reactor. As I said, this the setup that we wanted was going to be more flexible. And to be able to achieve it, we actually used mass flow controllers, which are depicted here, to provide the CO2 gas streams. And these were controlled by the computer. And we were able to change the flow rate and also the pressure at which we wanted to apply it. The feed of gas was then joined by the feed of the amino epoxide starting material and in a T mixer. And now the biphasic stream was then passed through a reactor, which was placed in a vertical configuration in order to favor the mass transfer and reduce the pressure drop of the system. And the reactor was placed inside a ventilated oven that we made to be able to control the temperature. Finally, the system was closed by a back pressure regulator, which was always necessary to keep some CO2 in solution. and then by a homemade autocollector that we designed, which was controlled using Python and a Raspberry Pi computer. And finally, we could get our pure compound. So this is how the setup actually looked like. In the view mode, you can see the mass flow controllers on the top. Here was the ventilated oven and the autocollector. And then the reactor and the degassing system that we designed to actually avoid spilling everywhere of the compounds. In terms of optimization, in this table are resumed some conditions that we tested, but not all of them. And here is the resume of the main condition that we found working for the most activated substrates. So the desired the use temperature was 80 degrees, since it was needed to boost the conversion significantly. So we could be with 10 degrees less, we could have conversion around 50% in comparison. In terms of the flow rate, we used 5 milliliter per minute of flow rate of CO2 and 0.1 milliliter per minute of flow rate of amino epoxide starting material. The pressure of the system was set at 5 bars, and the inlet pressure, so the pressure with the CO2 at which the CO2 was provided, was of 10 bars. We couldn't go above in the pressure of CO2, also in the pressure of the system, because due to the pressure drop that we observed, then we were not able to actually establish a flow. And we actually observed that the liquid phase tended to go back towards the gas line, which is actually a rather dangerous behavior. In terms of solvent, of course, methylethyl ketone is probably the best solvent when you want to use CO2 for this type of transformation. But since oxazolidinones had a tendency to precipitate inside the reactor or on the actually on the drops that were being collected, then DMSO was used as cost solvent. This was the best amongst the many solvents that we tested. But at the end, only with 6.5%, we were able to actually solve this issue. Here you can see the scope of the transformation, as you can see, was rather broad, and many functional groups were tolerated. In terms of the medium substrates in terms of activity, so we observed that an electro-withdrawing group in the para position was actually detrimental for their activity, and even increasing the reaction time by reducing the flow rate to 0.05, we still observe maximum 65% conversion. And when you compare this with the meta-substituted derivatives, you can see that with a similar condition, we were achieving 80% conversion. The worst substrate of all, though, was the orthometoxy group, which actually, at best, we were able to achieve 30% conversion. And this seems to not be related with the steric issues, because other bulky substituent didn't actually affect the reaction outcome, but it seems to be related more to electronic matter. I have to specify that all the experiments in the previous slide, so the scope, were performed with a fresh batch of catalyst. So just to check how a fresh batch would behave in this type of transformation with different substrates. What we wanted to do next was to prove the stability of the catalyst in a demo campaign. So we wanted to simulate what would happen if in a pharmaceutical lab, they would want to prepare a battery of these compounds using the same batch of catalyst. So what we did was the first day was to run one experiment with one substrate, so in this case, the parabromide derivative, and then to carefully wash the catalyst. So for 6 hours, just to have a clean catalyst for the next operation. And then the day after, we will start again with another derivative, and so on, so on. And you can see here in the column labeled as C1, this was the conversion observed with a fresh catalyst. And here in C2 was the conversion observed with this recycled batch of catalyst. And actually, what was interesting to see is that no deactivation was observed. It was true that in some cases, like here in entry 3, the conversion was slightly lower, but in other example, we actually observed higher conversion. So our conclusion was that the catalyst was stable. What we did observe, though, was that in some experiment, there was some variability in the selectivity of the transformation, which was actually surprising because base type catalysts act with a mechanism in which the aniline is activated by the protonation, and then this nucleophile is then able to attack the CO2, generate a carboxylate, which then will attack the epoxide, generating the product. But the other product that was observed was actually the carbonate, which is not possible to form with base catalyst and at these temperatures. What we actually discovered was that there was some sodium chloride in the resin, and this was discovered by SEM analysis, which probably due to the residual amount of water in the starting material was getting solubilized, generating the chloride anion, which was able to open the epoxide, generating an alkoxide that was then the responsible of attacking the CO2 and then re-enclosing, displacing the chloride. But this was actually an issue which was easy to solve just by carefully washing the reactor, just by carefully drying the starting material. Then this it was an easy addressable issue. You might also wonder why there was sodium chloride in the catalyst. So this is related to the way we prepare the catalyst, because we were using sodium hydrate to deprotonate an alcohol present in the catalyst, and then this was displacing a chloride present on the resin, and that's the sodium chloride. And probably since this resin was not swellable, then it was more difficult to remove the sodium chloride from the most hidden centers. So with this knowledge on hand, we also ran a 1-day experiment, so for 26 hours, in which we prepare toloxaton, which is an antidepressant drug. And we were glad to observe that our system was not only stable over small operation repeated over 2 weeks, but also over one long operation during 1 day. And as you can see here, so we could actually collect almost 1.6 grams after all these experiments. So in conclusion, we designed a more robust setup with that allowed us to have a broad scope. And of course, the main issue here is the productivity that should be improved further. But I have to say that this type of setup are easy to scale up. So just by increasing the pressure of the CO2 available in the lab, and then the size of the reactor and the flow rate of the starting material, then this reaction will be way easier to scale when compared with the tube-in-tube setup. In this fourth section, which is the last one related with the valorization of CO2, we decided to focus on the formulation of these anilines and amines in general. There were some examples in literature that employed NHCs and organic superbases to achieve this transformation, combined with a silane as a reducing agent. And depending on the catalyst, sometimes different silanes were observed. There were two main issues to address in this transformation, which were the selectivity between the formulation and the methylation, which we actually thought we could address by carefully coupling the silane reducing agent with our reaction, with our catalyst, and then the scalability. So there is a side reaction which is involved in this transformation, which generates hydrogen upon contact of the catalyst with the silane. And this could be tricky to scale up in batch, and that's why we wanted to to actually develop a flow chemistry approach with an heterogeneous organocatalyst for this. To do this, we first develop the process in batch to also study more the transformation. And in this case, for the screening, we were glad to observe that we could actually employ CO2 in a balloon with a simple vial to run the reaction. And this allows us actually to quickly screen all the reaction conditions. In terms of the silence, we started our study using PHMS, which is a polymeric type of silane. And unfortunately, what we observed was that there was no conversion when an heterogeneous catalyst was used. So this is entry 2, while entry 1 was with the homogeneous catalyst. This is simply explained is just by using a polymeric catalyst and a polymeric silane, then they could actually not interact, thus there was no transformation. We also screen many silane reducing agents that are commonly available in the labs, and all the alkylic silanes didn't give any conversion. When we then passed to the phenyl silane, we actually observed high conversion, but poor selectivity. So up to 20% of the dimethylaniline, which was actually not what we wanted to achieve. But then we were glad to observe that 3-methoxy and 3-ethoxysilane could go to complete conversion, nearly complete conversion, and with high selectivity. And at the end, we preferred to use 3-methoxysilane because it was slightly cheaper and was actually easier to retrieve in the market, while 3-ethoxysilane was more complicated. In terms of catalysts, by that moment, we already had a huge library of organic catalysts, organic supported catalysts available in the lab. So we screened them, and here are depicted the main results. Curiously, some of them could not achieve high conversion. In this case, for example, the polystyrene supported triphenylphosphine. And also the activity directly supported on the resin couldn't achieve very high conversion. I mean, we only observed traces of compound. All the other catalysts instead were proficient, but we ended up choosing the BU supported catalyst for various reasons. Of course, it was able to reach high conversion. It was relatively cheap when compared with the BEMP catalyst, but also as another advantage. And this was that it was anchored to the resin with a carbon-carbon bond, and this was preventing the leaching. Leaching that was actually observed, for example, when using the TMG-supported catalyst, and this was very easy to observe by LCMS. With the catalyst on end, we also screen the temperature, and this was not done for the optimization in batch, but more to collect information about a possible intensification in continuous flow. This because the reaction could already achieve high conversion at and high selectivity at 30 degrees, but to achieve high conversion in flow in reasonable times, you usually need to also increase the temperature to achieve high conversion. And what we wanted to observe with this experiment was that the selectivity was kept high also at this temperature. The lower conversion that was observed was for the way this reaction was run, which was actually not in an autoclave, but in a vial. So it was not possible to load as much CO2 as necessary. Furthermore, at 100 degrees, the solubility of this gas was way lower than in comparison with 30 degrees. And in terms of the silane equivalence, of course, since we were purchasing these reagents and also was not in that specific moment that easy to retrieve, then we wanted to reduce the equivalence, and we were glad to observe that we could achieve high conversion also at using 3 equivalents of silane. Unfortunately, we couldn't reduce it to 2. And this issue is probably due to the side reaction that I mentioned before. So part of the silane is wasted in the generation of hydrogen rather than in the actual reaction that we want. I talk about many conditions, so here I just summarized the condition that we used for the scope in batch. So a test tube plus a balloon, trimethoxysilane with 3 equivalents, and then polystyrene supported DBU as a catalyst, and 30 degrees of temperature. You can see here the scope of the transformation. We actually could achieve high conversion and high yields in most of the substrates, and various functional groups were tolerated for both aromatic and aliphatic amines. But as I mentioned, our goal was to have continuous flow transformation. So at the beginning, we thought, why don't we run the reaction the same way we run the formation of cyclic organic carbonates? So with the OmniFit column, a glass reactor, to run the reaction with the tube-in-tube setup. Unfortunately, what we observed was that with this type of setup, there was an increased pressure probably due to the formation of the hydrogen, and this actually made the reactor explode. Luckily, since this was a flow chemistry setup, this explosion was controlled. So just the reaction was damaged, the reactor was damaged, but everything was under control. So to actually be able to control this behavior, what we did was to change from a tubular glass reactor to a Teflon tube in which the catalyst was loaded as a slurry. And since there was also an increased pressure, we used an Agilent HPLC pump to push the solvent of the reaction acetonitrile into the stream. Since we didn't want to ruin this pump, we also used a preloading loop in which we loaded the sample. And then the rest of the setup was actually similar to what you observed I described before. So the tube-in-tube to saturate the stream with CO2. Then this tubular reactor to run the reaction at 80 degrees. And then a back pressure regulator to close the system. And an autocollector to collect the fraction. After a quick optimization, we could actually achieve very good conversion in the experiment, and you can see that the maximum productivity that we achieved was of 6 millimoles per hour, having a conversion of roughly 90%. But to actually study more the stability of the system, we settled more for a longer residence time, so 60 minutes at 80 degrees, to actually study how stable was the system. Because again, our main goal was to assess whether we could run this reaction for a long time and whether this type of reactor was safer in comparison with the previous one. And actually, thanks to this, we could run the experiment for roughly 500 minutes. Out of these for 5 hours at the steady state, so in stable conditions, and without losing any conversion or any selectivity. And at the end, what we did was just to wash the catalyst and remove it from the catalytic bed, and then test it in batch. And we were glad to observe that the catalyst actually retained its activity, and probably this reaction could be run for even longer times. So in this case, we could achieve a overall safer process in comparison to what was previously described through the intensification in continuous flow. And we had a maximum productivity of 6 millimole per hour, which is roughly 800 milligrams. And this could be actually easily optimized by changing, for example, the material of the reactor from Teflon to stainless steel. And this will be in this way, we will be able to actually withstand higher pressures and thus achieve also higher productivities. So this is actually not the general conclusion of the talk, but the general conclusion for the CO2 related part. So I hope I showed how we can use halide-free organocatalyst to do the valorization of CO2. I hope I showed that we can do it in a continuous flow. And in the future, it would be interesting to see more telescoped application of these carbonates and carbamates for the synthesis of drugs. Plus, it would be also interesting to see a combination of these heterogeneous organocatalysts with some photochemical and electrochemical processes. Recently, I saw that photochemistry was applied for the reduction of CO2. So I guess we are coming closer to the point in which we will have this combination of techniques. Now this is the new section that I added because this was also is related to the use of gases in continuous flow with the setup that we already showed. And that is also related as an evolution of what is happening with what was developed. So this actually comes from a collaboration of our group with the groups of Montserrat Dieguez, also based in Tarragona. And what we wanted to achieve was an asymmetric hydrogenation in flow with an immobilized iridium catalyst. This type of reaction is interesting because in an industrial setting, asymmetric hydrogenation is with metal catalyst is one of the most powerful transformation to generate chiral centers. But in this case, what is limiting the application of the heterogeneous asymmetric catalyst is their recyclability. And this is why we focus on this. There were many reports of metal-supported catalysts, but in general, two main approaches were used for asymmetric hydrogenation. One very interesting approach was this reported by Agustin, in which they were using some polymeric type of acid into a aluminum oxide support to have an ionic charge on the support, which by electrostatic interaction was actually keeping the rhodium catalyst loaded in the support. The main limitation of this approach in the reduction of alkenes was that activated alkenes must be used in this transformation to achieve a proficient system. Also interesting, there was the covalent approach of immobilization developed by Kobayashi, but in this case, he was supported at non-chiral catalyst into a polystyrene resin, and then using an homogeneous trip to actually be the source of the chirality of the system. And even though he was able to recover the trip at the end of the transformation and reuse it in future transformation, this looked laborious. So what we wanted to do was actually to design a simple cat ligand, which was easily attached to the resin and gave also already a source of chirality to the transformation. Furthermore, we wanted the asymmetric side to be farther away from the support because this could actually distort the transition state and does not facilitate the transformation. To do this, we develop a simple synthesis, which is actually as long as the synthesis of the homogeneous catalyst. And in this case, you can see that we started from a chiral epoxide loaded into the resin by simply using sodium hydride in DMF, open it with this 2,6-dimethylthiophene, then simply attach the phosphine ligand, and then inserting the iridium to generate the catalyst. And here you can see the loading of the catalyst we develop, expressed in millimole of iridium per gram of catalyst. On this point, I would like to underline two main points. So, of course, our synthetic approach was simple, but probably also due to this simplicity, then we generated a catalyst that was also very stable. And actually, this was prepared and used after 3 years and still retained its activity, which is already a remarkable feature. So, of course, after preparing the catalyst, we wanted to screen them. We screened them first in batch, and we were glad to observe that we could achieve high conversion and high enantioselectivity in the transformation. Also, when compared with the homogeneous catalyst, which is entry number 4, compared with entry number 1, 2, and 3. And at the end, we settle with catalyst 2 because of the loading and the easy to prepare it. And we perform some recycling tests in batch with these different substrates. We did lose some reactivity here, but not an anti-selectivity. And this was something that we hoped a continuous flow approach could solve. And this because usually catalysts, when are used in flow, they suffer less manipulation, and thus the lifespan of the catalyst is increased. Another thing that made us thought that a continuous flow approach could be beneficial in this case is that no iridium leaching was observed from the resin, and this might mean that we were just probably losing the ligand from the catalyst in the resin. We were glad to observe that in continuous flow, we didn't lose any reactivity once the experiment were run. We observed high conversion and high anti-selectivity with various substrates, which were in part more challenging when compared with previous developed scope of reaction. And then we could have up to 70 grams per millimole of iridium produced per day in terms of productivity. What is also nice is that some of these compounds, such as LG121071, present biological activity. In fact, is a drug precursor, which is actually LG could be prepared from S4, which is what we prepared. And then other compounds such as tumeron and curcumin, which are used in the cosmetic industry because they are fragrances with spicy odor. They could be prepared from substrate S7, which was prepared in this fashion. What we wanted to address then was the recovery of the activity. So what we observed was that when the catalyst was stored, lost some activity, even though during the transformation, it didn't lose any activity for 2 days. So this was already suspicious. And plus, this was combined with the fact that the catalyst at the beginning of the experiment, you can see here on the left, was red, while the catalyst after the experiment was yellow. So this sometimes doesn't mean much, especially in organocatalysis, but when you have a metal complex could be suspicious. And thus we thought that this change of color could be due to the loss of the COD ligand. And what we did after the reaction was just to flow the COD first with hydrogen and then without hydrogen. And we observed first that the color was recovered, and then we also observed that the activity was recovered. And thus the final recovery protocol was that after the reaction, the code was added again, and then the catalyst was dried this time. And after drying, we observed that after 2 weeks, this could be used proficiently in the transformation, which is also a very powerful feature for this catalyst. So now I'm reaching the conclusion of the talk. What we wanted to do was to develop a synthetic method to anchoring in the past homogeneous class, now heterogeneous, which we did. This type of ligand is also highly flexible and versatile, since when different substrate would want to be tackled, it's also possible to modify its precursor to achieve a better transformation. And thus it's going to be easy to build a battery of catalysts to screen. We did use it efficiently in continuous flow for the asymmetric hydrogenation of olefins. Some of them important from a pharmaceutical point of view, some of them from in the cosmetic industry. And then we always had a long reaction time in which the catalyst was stable and the system was performing well with high yield and high N anti-selectivities. And finally, I would like to thank the organizing committee for having me here discussing this chemistry. I would like to thank all the audience for listening. I hope there will be questions. I would like to thank the funding agencies that helped me during with the funding of this process, and of course my supervisors at the time, so Miguel Pericas and Professor Miguel Pericas and Professor Nadia Clay, and then of course all my team members, co-workers, lab mates with which we share so many experiences, and without them would have been way more difficult to achieve this. And finally, also, if you would like to contact me, I always accept requests on LinkedIn, or if you have any other more specific request on the chemistry, or I don't know, like life in industry, you can contact me by email or also by LinkedIn. So thank you all.
Hello.
Hello.
Hello. Hello.
Hello.
Hello. Hello. Thank you, Dr. Nicola Zenda, for the continuous flow catalysis for the valorization of the carbon dioxide. And the topic is open for the discussion. So I would like to request all the participants here offline and online to have some, if you have some query, you can ask for the questions. So we can go for that. Online questions. Yes.
Sir, first of all, your lecture is so engaging and very good. I would like to ask, is the valorization of carbon dioxide applicable only to secondary amines, or it can be extended to other functions?
So the question actually cut, so I couldn't listen to all of it. What I understood is that you're asking whether we could apply only the valorization of CO2 to amines or to other functional groups.
Okay.
So actually,
Nicolas, sir, I would like
Yeah.
to ask one question. Is the valorization of carbon dioxide applicable only to secondary amines, or it can be extended to other functional groups as well?
okay, thank you. Now is the audio is clear. So we can extend it to other functional groups. So you can have a or you always need a nucleophile as a reacting partner. And this can be an amine, but it can be also an oxygen or a sulfur atom. But you can also have carbon nucleophiles. So for example, you can see here in this scheme that there are transformations. And actually, this is not limited to the carboxylation, because if the molecule is functionalized in a different way, then you can also have a cyclization event. And furthermore, depending on the substrates, you can also have cascades. So usually, for example, if you have a carbonate nearby a double bond, then you can easily functionalize it afterwards. So this increases the scope of all the transformations.
Hello. I would like to ask online participants if you have any questions, they can put up in the chat box.
Hello, sir. I have one query. In your discussion, you said okay, sorry. Sir, in your discussion, you said NH activation is with MEK. What is the role of MEK in the activation of NH proton?
Oh, okay. I was referring to this in this here actually, for example. So what I was saying was that methyl ethyl ketone is very important in this transformation, but its role is not in the activation of the aniline nitrogen, but it's very important for the solubility of the CO2 into the reaction mixture. The amine is activated by the base catalyst that we were using. So in this case was the TBD. So which I can show you here in the first slides. So in that case, the base would just deprotonate the aniline generating the nucleophile, that is the coupling partner for the CO2, but the methyl ethyl ketone would assist only by solubilizing the maximum amount possible of CO2. It possibly have other effects in the stabilization of the anion or in how close the compounds can reach, but mostly it is accepted that its role is for the CO2 solubility.
Once again, I would like to thank Dr. Nicholas Zender for answering our questions. So I would like to mention special thanks to Dr. Nicholas Zender from the Switzerland for mentioning the importance of the CO2 utilization through the flow chemistry, highlighting the applications of the organic catalyst and the halide-free synthesis of the glycerate carbonate under the continuous flow, and also mentioning the catalyst screening and showing those is reactions of carrying out the 4 cycles, and which will require about 13 hours of work there, and in the, including up to the 5 sections, whereas the mention is thorough work and which has been marked in the prestigious journal right from the UK. So once again, I would like to thank Nicholas Zender for delivering this session, a wonderful session, sir. And also, I would like to mention Department of Chemistry, MSG College, for giving me a chance to chair this session. Thank you.
Thank you so
Thank you
much.
all.
Once again, we sincerely thanks to our esteemed speaker, Dr. Nicholas Zenda, for sharing his valuable knowledge with us. Also, very much thankful to Dr. Ashish Gajbia sir for chairing this session very expertly. Now, with the kind permission of coordinator, we concluding this section second. Now, moving towards the session third, I would like to invite Professor Dr. Vivi Kadam sir to as a session coordinator to continue third session. For the third session, we have Dr. Santosh Maske sir from NCL. I would like to invite Dr. Vivi Kadam sir to introduce our esteemed guest, Dr. Santosh Maske sir.
What is it? Good afternoon, one and all. It is my privilege to introduce our distinguished speaker for this session, Dr. Santosh Maske. Dr. Maske is currently serving as a senior principal scientist F at Council of Scientific and Industrial Research, National Chemical Laboratory, Pune, and is also a professor at Academy of Scientific and Innovative Research, ICER. He obtained his PhD in chemistry from CSIR NCL under Savitribai Phule Pune University, Pune. He brings with him extensive national and international research experience, including postdoctoral work in United States at Wayne State University and Illinois Institute of Technology, and in Germany as an Alexander Johann Humboldt Fellow at University of Hannover. He has also been a Ramanujan Fellow at Department of Science and Technology, Government of India. Dr. Muske research focus on development of novel synthetic methodology and their applications in the synthesis of important APIs and KMS and bioactive natural products with strong relevance to the pharmaceutical and material application. He has made significant contribution to the process development, including industrially important molecules such as rosuvastatin and montelukast. He has honored more than 75 publications, hold 90 patents, and has successfully guided numerous PhD, MSc, and project students. His work has received wide recognition, including the Sipla Hameld Best Process Development Award, Scientist of the Year Award from National Chemical Laboratory, Pune, and several prestigious national and international fellowships. We are honored to have him with us today. I now invite Dr. Santosh Muske to kindly deliver his talk. Thank you. And I announce chair the session, Dr. Vishnu Adole. Dr. Vishnu Adole is my proud, he is my student, and he is a research scholar. Research paper published by Mr. Vishnu Adole, Dr. Vishnu Adole, more than 1,400, and now he is a listed 2% scientist in worldwide. So I will announce Mr. Dr. Vishnu Adole to chair the session. Now I request Dr. Muske sir to continue his talk. Thanks.
Good afternoon, all. I hope my slides are visible properly. Can you hear me?
Yes, sir, it's visible.
Okay. Yeah, thank you, Dr. Kadam, for the kind introduction, and all the dignitaries, Dr. Subhash Nikam, sir, Principal of College, Dr. Shinde Shinde and other organizing committee, and Dr. Vishnu Adole, the chair of this session. So actually, I was contacted just 2 days before, so my slides may not be that good as the previous speakers. So excuse me for that. When I was informed, I wanted to see know about the college, and so I visited the website as well as I saw the flyer. So it was really interesting to see and know about this college started by Sri Hire, the educationist, and he started in 1959, which is amazing because it is just few years after the independence. And also, it was nice to know that Dr. Pula Deshpande, P.L. Deshpande, was the first principal of this college. And also, the labs are well equipped with funding from DST and other funding agencies. So thank you. It's an honor for me to present in this conference, although it is a last minute invitation. But thank you for the invitation. So my presentation is basically for both like graduate students, undergraduates, or postgraduate, and like faculties who are MPhil or doing their PhD or completed PhD. So it's a mix of work as well as some general slides. The general slides will be useful for students who want to pursue research as a career. So the intention of such international conferences is to make students from remote places interested in research, taking research as a career. So I will start with some information about the institute where I work. So it's National Chemical Laboratory, NCL Pune. Many of you might have heard about it. So it is one of the laboratory of CSIR, which is Council of Scientific and Industrial Research. There are such 36 laboratories working in different areas of sciences. So this lab was opened in the 1950s, and it was opened at the hands of Pandit Jawaharlal Nehru, who was then Prime Minister. And that time he said this sentence: the purpose of this laboratory is to advance knowledge and to apply chemical science to the good of the people. As he rightly said that time, this laboratory really delivered, and this is one of the laboratory which is responsible for all the pharmaceutical industries in India. It acted as a catalyst, and now also NCL, now also NCL is supporting the industry as well as doing basic research. So we have 6 different scientific divisions, as I have mentioned here. I work in organic chemistry division. So these divisions also collaborate with each other, the scientists from this division, and we also publish, we also work with industry and bring a revenue for the country as well as develop new technologies. So we have, other than administration and accounts and other sections, we also have a technology management group as well as intellectual property group. So these are our scientific supports sections. So a few things which happened recently at NCL, I'm giving under different sectors, like under pharma sector, this technology for continuous flow synthesis of azelaic acid was developed, and it has been given to the industry. The technology has been transferred to the industry. Then the rosuvastatin, which is for used for to lower the heart disease risk. So for this, one of the key step was developed in NCL. This is in my research group. Then in biotechnology sector, enzyme was developed for cyanation, and this technology is also transferred to the industry. So if you look at the other sectors like agro sector or health sector, NCL has delivered in all the way in different areas of sciences, including the zebrilic acid process, and it was given to Godrej many years back, and still it is being used. And you might be aware that the crop production doubled or tripled after the use of this gibberellic acid. And in health sector, oxygen enrichment unit or zeolite for oxygen concentrator, and now it is being tested in MiG aircrafts. NCL also worked in a polymer division, defense sector. You might have heard about the BrahMos missile system. The 14 for BrahMos was developed by NCL, which is high temperature resistant polymeric material, which was necessary at that time, and the import was banned for India. So NCL could develop that technology and transfer to our military. In energy sector, we have technology for dimethyl ether. Then we have technology for fuel cell, which is being tested in buses and other vehicles. So coming to our division, which is organic chemistry division. So this was one of the first division which was started at NCL, and it actively helped the industry, pharma industry and the chemical industry in Maharashtra and India. So I will not go into details of all these things like how many scientists and students and so on. But I would like to tell you that we have one of the few of the best scientists here working in organic chemistry division, best known organic chemists. And we publish every year at least 100 papers per year. And we also file patents and earn ECF of 300 lakhs rupees per year. We have dedicated NMR facility, analytical and preparative HPLC, mass, HRMS, and whatever is required for organic synthesis, we have it. We also have separate hydrogenation, sulfur chemistry, and kilo lab facilities for process development. So at organic chemistry division, the scientists work in different areas of research, such as total synthesis of natural product, then process development for APIs, KSMs, and agro products, as well as material chemistry, chemical biology, synthetic biology, biocatalysis, and so on. So on the sides, as you can see, I have shown some products, and these are being used in the market currently as well. So these processes were developed at NCL. In addition to these research areas, which I have showed in the center, NCL is also actively working on, means our division is also actively working on peptide chemistry, photochemistry, electrochemistry, and flow chemistry, which started recently. So on this slide, I have kept the structures and name of some of the drugs and drug intermediates for which NCL has developed technology and transferred to the industry. The list is not exhaustive. This is just representative list, and many more such drugs and API processes have been transferred to industry. So this is my research group at NCL. These photos are not really latest one. So what we do is we develop novel chemo, regio, and stereoselective carbon-carbon and carbon heteroatom bond formation reactions, and their applications in synthesis of bioactive natural products, APIs, that is active pharmaceutical ingredients, KSM, that is their key starting materials, and new chemical entities for various applications like for developing new bioactive molecule or for advanced materials. So what we do is we work in different area of different organic chemistry tools like CH activation. Then we also work in organocatalysis using NSC catalysis catalyst. Then transition. We also work in transition metal-free methodologies using arine chemistry, decarboxylative carbon-carbon and carbon heteroatom bond forming reactions. We also work on total synthesis of bioactive natural products, like first total synthesis or important bioactive natural product, which is recently published or isolated. And in addition to this academic type of work, we also work closely with industry and to solve their chemistry problems or develop process for particular state. So I thought that there are participants in this conference which are like graduates or undergraduates, postgraduate, and some MPhils also. So I will start with something simple. So how the research in organic chemistry works. So they will also get inspired. They will also understand the process and what I'm telling in my next slides. So as you know, that the first reaction in organic synthesis was reported by a German chemist, Friedrich Wöhler, in 1828, wherein ammonium cyanate on heating provided urea. Until that period, like 1820, it was considered that such type of organic compounds can be synthesized only in the living system. Means only living beings can synthesize these molecules, and it cannot be synthesized in laboratory. But Friedrich Wöhler's this report of synthesis of urea changed everything, and you have you know the progress that is taking place in this research area. So what happens first is a hypothesis wherein we propose that or think that we can do this reaction, particular reaction. I have just given example of paracetamol here, and let's say that we want to develop a new catalyst which can give directly from chlorobenzene with single step paracetamol. So with this hypothesis, when we start, we plan some reaction, and then in first few attempts, whatever result we get, we analyze them well. Then if the result is expected, definitely then we can further take it for optimization. Or if the result is unexpected, we can analyze and see what is giving this different result than expected. But such an unexpected result is called serendipitous result. And these are also sometimes more important than what we expect. So we can explore it further and report it, file a patent if it is totally new. Then this observation and analysis while doing the reactions are very important. So how we follow these reactions is the first source is TLC, thin layer chromatography, which we can see the starting material is consumed, not consumed, reaction is progressing or not, or we can also use GC, HPLC and other methods. Once we know that the reaction is happening and we are getting either the desired product or something completely new, we can isolate and then characterize. For organic compound, we know that proton NMR 13C, IR, and GC, HPLC. There are so many methods to characterize such compounds. And once the structure is confirmed and the proof of concept is ready, that means now whatever we hypothesized is working well, or we are getting something different. So we know that if I take this reaction condition, I will get this particular product. So then the student will start optimization of the condition. So he will improve the yield, change the solvents, reaction time, temperature, and there are so many different parameters. The first important criteria is to see whether you yourself are able to reproduce the result or not. So once that is confirmed, you can think of generalization or substrate scope, which is very important because that shows that whatever you have developed is not only limited to that particular substrate, but it can be also used for different substrate with different substituents. And if the molecule is of industrial importance, we can also think of scale up. That means we can go from gram scale to 100 gram scale up to kg scale. Of course, more than kg is not possible in organic chemistry lab. We can take help from chemical engineers. But while doing all these things, we have to keep in mind the safety aspects of all the reactions that we handle, like seal tube, it can blast anytime, or the chemicals such as benzene, for example, which is carcinogenic. So we should not touch it with bare hand. Basically, we should avoid such chemicals use because it can lead to some diseases. Then reagent like azides, they can blast anytime. So we have to take care of all these parameters and develop the process, which can be then taken up by industry. If your product, whatever you are getting, or the reaction that you have developed is of industrial importance, you can file a patent. So the process for filing patent is to first, whenever you get a correct result, and you can see that it can be generalized in at least one or two substrates, then you can file a provisional patent, which the filing number, you'll get provisional filing number. Within 7 to 15 days, you can get the number, and after 1 year, you file a complete. So it's always good to protect a new reaction or a new product and its application. So followed by this, once you file the patent, you can go for publication. So as you know, there are different types of journals, different societies like American Chemical Society or Royal Society of Chemistry, Willy, and so many different publications are there. Nowadays, there are many open access journals also, but you have to be careful while publishing. there are many predatory journals which take money and publish without any review. And especially to avoid these things, in India, we have a UGC care list where they have given the journal list wherein Indian universities can publish, and we cannot publish in any other journal which is not there in the UGC list. So this was about general what happens in organic chemistry research. Just to give an idea to graduate or postgraduate students. So before going to my work, I would like to tell you something about the concepts in organic synthesis, which I will use in my next slides. So you all know what is catalyst, so I need not tell about it. So it is the substance which catalyzes or increases the speed of reaction or make it mild, and how it works, but it will not be get consumed in this process. How it works is it lowers the activation energy of the substrate, and that's why the reaction takes place faster. So the other terminology which we use is pre-catalyst. Pre-catalyst is that means before actual catalyst. So these are the species which are stable, easy to handle. We can store in bottles. For example, I have given here example of palladium tetrakis, which is actually the catalyst used for many coupling reactions, as you might have learned. But the actual catalytic species is PDPPS3 thrice, which is formed when you add this in solvent. So the reason why we use pre-catalyst is to make it more easily. We can handle it, we can store it. Then metal catalysis, again, I need not tell you, there are many metal catalysts, like even palladium is used for a reduction purpose or coupling purpose. The zinc, many other catalysts can be used for various organic transformations. But nowadays, there is a concern about not only the environmental effect, but also the cost of this catalyst. So novel ideas like biocatalysis or organocatalysis, photocatalysis, all these areas are getting more importance. Although this biocatalysis is not a new idea, but nowadays, looking at the environmental effect, this use of enzyme or biocatalysis is becoming one of the prime importance, and industry also would like to add at least one step in their 5-step sequence. One of the steps should be biocatalysis. In this organocatalysis, as you know, recently, not recently, in 2021, Benjamin List and David Macmillan received Nobel Prize in this chemistry area. And herein, the proline, which is naturally occurring amino acid that perform these aldol reactions. So organocatalyst means organic molecule doing the organic transformation. And this area is also picking up in industry sector as well. The other way to reduce the environmental impact is to use photocatalysts. For example, titanium dioxide is used for water treating, but for organic transformation, there are many metal-based catalysts, or we can use organic compounds or dyes for this purpose as an activator. In this retrosynthesis, this terminology is used to look into the structure of the target that you want to synthesize and see how we can dissect the molecule or the bond, disconnect the bond, and we can think of starting with the simple starting material which are commercially easily available. So that is the retrosynthesis. Then other terminology is Poland reaction. You might have learned benzyne condensation, wherein sodium cyanide is used. So this aldehyde, benzaldehyde, converts to benzoin. So you can see in one of the aldehyde is converted. It is an electrophile, but actually it is converted to nucleophile, which reacts with the other molecule to form benzyne. That means change of polarity from electrophilic to nucleophilic. Then other terminology that I will use is carbene or n-heterocyclic carbene. Carbene, most of you know about it. So the first hypothesis was reported by this Bruckner, Edward Bruckner, in 1903. and wherein he treated ethyl diazoacetate with toluene, and he proposed that probably it goes via carbene. Later in 1912, Staudinger, who got Nobel Prize in 1953, he reported cyclopropanation of alkenes with diazomethane. So basically, these carbenes, they are in two forms. One is singlet, and the other one is triplet. So the triplet are high energy forms. So you know that there are different types of carbene, Fischer and Stock carbenes reported. So these carbenes have been used in the literature as a ligands to different metals. And you might have heard about Wilkinson catalyst, for example, or you might have heard about Grubbs catalyst, wherein the metal is ligated with the carbene. So our in this area, we work on N-heterocyclic carbene in organocatalysis. So N-heterocyclic carbene means there is a nitrogen in the heterocyclic carbene, and on the adjacent carbon there is a lone pair of electron. So basically, if you see the carbon, which is central carbon, so it should have 4 different bonds, but there are only 2 bonds and 2 electrons. That means 2 electrons are less to complete the octet. So it is actually an electrophilic carbon, but due to presence of nitrogen, adjacent nitrogen, it becomes a nucleophilic carbon. And this reactivity has been very synthetically useful, and it has been used in several transformations in the literature. Initially, it was thought that we cannot isolate it, but Adiunger reported the first report where with the aramantyl ring attached to the nitrogen, he could isolate the stable carbene. And to use these carbenes in synthetic transformations, we need to store them in a stable form. We cannot store this. If aramantyl group is not there, this carbene will not be stable. So to keep them stable, what we need to do is we store them as their salt, corresponding salt, which is called NSC pre-catalyst. So pre-catalyst is the species which convert to the catalyst in the system, as I told before. So this NSC catalysis we are using in our organic synthesis, and we form different novel scaffolds or known scaffolds with more efficiency. So with these concepts, I'm sure it will be easier to understand what I'm going to present next. So organocatalysis with NSC catalyst. So the first work which I'm presenting here is NSC catalyzed allylation of aldehydes with MDH carbonates. And further, we have shown its application in synthesis of the drug molecule, but a racemic synthesis of drug molecule sacubitril. Additionally, we observed other interesting product also, but I do not want to give that complexity here. As you can see, the hypothesis was to take the aldehyde, which on treatment with the NSC pre-catalyst will form a Breslow intermediate. This is called as Breslow intermediate. This is the Breslow intermediate, which is actually a nucleophile which reacts with this alkene, and this Bock group is eliminated. So essentially, what we wanted that this alkene should be retained, and we should have a carbonyl. That means 1,4-dicarbonyl compound with alkene, so that we can reduce both these groups. And there are many such natural products and drugs reported in the literature which can be synthesized using our strategy. So this was the hypothesis. With this, we started optimization. So we prepared several different NSC catalysts as shown here. Different types of different heterocyclic scaffolds we prepared, and they were tested under this condition. And we could, in one of the conditions where we use cesium carbonate, we could get yield up to 76%. And once the product was completely characterized and the reproducibility was confirmed, we then planned for the substrate scope. As I said, once we develop the reaction, once it is optimized, we can see whether it works with other substrates or not. So we could do that, and many substrates were working under this condition, and it was suitable for even heterocyclic moieties or this iron containing substrate, even alkyl substrates also, though the yield was less. So at this stage, the generalization was truly established with this NSC, and we are interested to see whether we can really show its application in the drug sacubitril. So this we planned the synthesis starting from the MBH carbonate, that is Morita Bellis Hillman carbonate. The previous speaker also used this as a substrate. So this is very easy to prepare, starting from acrylate and formaldehyde. That is known as basically Morita Bellis Hillman reaction, and then it can be protected with Bock group. So this aldehyde was prepared from a corresponding acid, which is commercially available. We followed esterification followed by reduction and oxidation step for better yields. However, direct reduction of acid to aldehyde is also documented in the literature. So our NSC, which I have shown on the previous slide, it worked well. So although this is not really a scaling up, or this is not really the optimized condition, but we wanted to show the proof of concept that our developed method can be utilized in really drug molecule. So this is the key intermediate which is being used right now also for the synthesis of sacubitril. The further we showed that with we can do reduction followed by conversion of OH to N3 with NaN3 displacement. First, of course, we need to make it good living, and then N3 can be converted to corresponding amine and reacted with succinic anhydride to get the sacubitril in 96% yield. So if you can count these steps, so hardly 4 to 5 steps are required to get this drug molecule, which otherwise requires more number of steps. But this is a racemic synthesis. Now we are working on enzymatic reduction of this alkene, that is reductase, and we are also working on transaminase type of reaction using that enzyme. So that will give a chiral sacubitril molecule. And this work is also under active progress. So this is published in Organic Letters recently. So after developing that, means showing that it works, our method works, NSC catalyzed method, we plan to show that it can be also useful to do it in the continuous flow synthesis of sacubitril. For that purpose, first we wanted to show that this proof of concept on model substrate. So we selected this aldehyde and this MBH carbonate. Here, this is the schematic diagram of this flow chemistry unit. And on the right hand side, you can see the actual photo. We have used here the syringe pump, which can, these are the two syringes where both the substrates are kept along with the catalyst, and then it passes through. And here is a coupler where it mixes, the mixer, and then it comes out and we can collect it. So if you look at our previous batch reaction, of course, this is on small scale. So on batch reaction, it was taking 6 hours and we are getting 40% yield. But within first 2 attempts, we could do this reaction, and in getting 46% yield, slight improvement in the yield. But you can see the reduction in time. Within 15 minutes, we could get the similar or better yield than the batch process, and the TLC and shows that it is cleaner reaction than the previous method, that is batch process. So this is how engineering sciences and biological sciences, all these sciences, along with organic chemistry, they develop novel methodologies of manufacturing the industrially relevant molecules. The next work is about organocatalysis again, and based on N-heterocyclic carbene. wherein we hypothesize that we can synthesize a symmetric synthesis of succinimides, which are very commonly observed in natural product as well as drug molecules, and giving a single step method to such molecule, which further can be converted to anhydrides or diacids and further transformations to basically it can act as a building block for many different kind of drug molecules, which is well reported in the literature. So we hypothesize that we can take alpha beta unsaturated aldehyde, and due to high reactivity of this cis alkene, this amide, probably it will react through the beta, means alpha carbon. That means enolate will be generated with this NSC, and it can then Michaelad this at this carbon, which is more electrophilic, as it is beta to the ester, and it should give the desired target. So we planned the reaction accordingly with these two substrates, and this NSC3 showed that this is the best NSC which can give good yield and very high distereoselectivity and enantioselectivity. As you know, asymmetric synthesis is one of the important area in organic synthesis because we can get selectively one isomer which may be more active in case of drugs, and that's why it is important. So we screened several other NSCs as well, and the best yield was obtained, the condition was optimized, and reproducibility was also checked. So this work we have not published yet. After establishing the structure and reproducibility, we also showed the substrate scope. It works very well with different kind of substrates, electron donating, withdrawing, or heteroaromatic, alkyl, and so on. And interestingly, the enantioselectivity and diastereoselectivity is always more than 90 or 95, which is very interesting part of this work. Additionally, we have shown that the reaction also works well on gram scale, retaining the E as well as diastereoselectivity. This is the third work I am presenting on organocatalysis, wherein now instead of NSC, we are using organophotoredox catalyst, which is riboflavin based. It's acetylated riboflavin as a catalyst, and simple blue LED was used for this work. So we propose that probably we can take such acid, proline based acid, and under photocatalytic condition and in presence of oxidant, we should get iminium ion, and then the hetero atom should add to the iminium. And so we started our reactions. So we tried few reactions with different metal as well as organocatalyst. And interestingly, riboflavin worked very well, and we obtained 90% yield of this product when the reaction was performed on 2A to obtain the cyclized product 1A. So that means our hypothesis worked well. So we wanted to show its generalization and application in these are two of the drugs in clinical trials, and these are well-known quinozoline-based natural product, bioactive natural products. So we could show the substrate scope. We took different type of substrate, all electron withdrawing, heteroaromatic, and so on. And we also showed that we can form a hybrid molecule. This is actually a part of diphenyl drug. So we could couple with the proline, and it may have better activity. So this activity checking also is part of our work, where we give the molecule to the biologist for screening, and it is under screening currently. So we showed that we can not only need proline, we can also take other amino acids, and that also works well. If we take the chiral substituted proline, we can get also the good diastereoselectivity up to 4:1. So overall, with different type of substrates, it worked well to give the desired product. So we showed that NH, SH, and OH, all these three different types of heteroatoms can work and give the corresponding cyclized product. However, in case of sulfur, we observed a little less yield as compared to nitrogen and oxygen. And as we do in our group, we always show that whatever we have developed is really applicable to some active molecule or at least a natural product, bioactive natural product. So here we have shown that our method can be used for the synthesis of these two preclinical trial drug candidates, and which starts with commercially available starting material like this trimethoxy acid, which is then deprotected and then esterified, and the selective protection of this OH is done. Then we can again hydrolyze it and this coupling to get our ester, which on hydrolysis gives the acid, which is the desired precursor for our reaction or our methodology. And on this substrate, the reaction worked well. However, the reported yields are also in the similar range for the way they have done is multi-step synthesis. This is also multi-step, but compared to their number of steps, our number of steps are quite less. This is the last one in catalysis. So I told you that we use organocatalysis, and wherein we have used N-heterocyclic carbons. Then I showed the photoredox based catalyst, which is also organic compound, and then biocatalysis. So this enzymatic chiral resolution we planned, and for that purpose, we were actually working on development of method for thiazine moiety, and we hypothesized that we can take this thioamide and react with this MDH carbonate to get the racemic product, and which can be then we can do enzymatic resolution to get separately two isomers. So this is the intermediate that we thought that it is forming, and really we could isolate and see that it is forming, and but not in high purity because it is highly prone to cyclization, and then in situ it converts to the thiazine moiety. And this happens in presence of silica. So that slight acidity is sufficient to cyclize C to D and get this thiazine moiety, which is commonly observed in cephalosporin class of antibiotics. Once the method is set, and the characterization is done, reproducibility is checked, we could generalize the substrate scope, and we could show that it works with the different type of substrates. Of course, when we do this reaction, it's not that it works with all the substrates. So you can see here we have taken pyridine substrate, and that didn't work well in this case. So the next target was, the challenge was to do resolution of this product, our product, so that it can be used for the asymmetric synthesis of the desired target molecules or analogs of cephalosporin. So we thought of using CalB enzyme, which is known to hydrolyze esters. So in this case, when we tried the reaction with the buffer, interestingly, what we observed is one of the isomer remained unreactive and the other isomer got hydrolyzed. So we got very high, more than 95% enantiomeric excess in this case. So enzymes are biocatalysts. Basically, they are proteins which are stable at particular temperature, up to particular temperature, and in particular buffer condition. So we could use that in organic synthesis, and we could show that we can do resolution, and we can get both the isomers of this thiazine moiety. Now, I would like to share with you two things, two success stories which we have developed in our lab. These two things are relevant to industry. So in industry nowadays, peptides are coming back as a treatment in pharmaceutical industry. So this natural or unnatural amino acid synthesis is becoming more important. Here I have shown the structures of drug molecules or natural products which contains this alpha methyl proline. And on the right hand side, you can see the different methods that are available. So there are number of steps are high. The starting material is complicated, or the starting material is highly expensive, like this aldehyde, which is required here, or a complex starting materials are required, or which goes waste after the reaction is complete. So we wanted to plan something which will use the chirality of the substrate itself, as well as there will be no loss of atoms. So there is a term called atom economy and time economy. So atom economy means when whatever we start with, we retain, we don't lose anything from that. So in this case, we planned in such a way that there is no loss of any atoms in this synthesis, and it will be faster as compared to the reported synthetic methods. So this is what we planned, and we started with simple proline. So there are two ways to convert this proline to dimer. So in one of the way, we can make it convert it to ester corresponding with SOCl to methanol. We can make a methyl ester, and then on heating at 45 degree for it can be converted to dimer. And we could do this reaction up to 20 gram scale, so that we can report that it is a scalable approach. We also showed that instead of going via ester and then cyclization, we can directly go from proline directly to A with this new kind of reagent reported in the literature. And in this way, that will flows. So that can give up to 60% yield, and the purity of the material is also good. So there are two ways by which we can form this dimer, retaining this chiral center. Because what we observed is when we heat it more than 45 degrees, we see that there is some loss of chirality of these carbon centers, which is alpha to these carbonyls. So with this dimer, then we planned several reactions. Initially, obviously, we tried NBT lithium and many other conditions, but we could not get dimethylation. Always we used to end up in monomethylation. Then we could optimize to get dimethylation, but the cost-wise, it was not economically viable. Later, we also tried with potassium HMDS and sodium HMDS and methyl iodide at various temperatures, and this was the condition which gave the best yield. So then this dimer was further cleaved using SCl. So we tried for this also, we suffered a lot. Actually, initially we tried concentrated SCl and nothing was happening to the molecule. So when we diluted, we started observing the product. So we diluted further, and at 6 molar concentration, we could get this molecule. So this work was really appreciated by many, and recently in SynFact also it has been published by Dirk Troner with a nice comments about this work and its scalability and industrial applicability. So this work is published in OPRD journal, which is one of the journal which industry people like to read. So we are now working on using this as a starting material and synthesize torphinolite as the this as a target. The reason is this is used for Rett syndrome. However, this is neglected, one of the orphan drug, because the number of patients are less. So industry is not ready to synthesize, and we want to develop that process. Though some of the steps will be reported one, but we want to hand over this process to industry so that they can produce it and make it available for the patient groups. The next work is this Montelukast API. This is commonly prescribed the drug. I'm sure all of us have consumed it at one type of once at least in our life. So this Montelukast, or also called Singulair, is used for asthma and symptoms of seasonal allergies to the tract. So India is the largest producer in the world. However, the KSM which is required for this synthesis is imported from other countries, and that's why though India is the largest producer of the drug itself, this we depend for this on other countries, and that's the reason we wanted to develop a process based on the literature. We saw that we can synthesize by using following these steps. So of course, this molecule is quite old molecule. In 98, it got approval, but you can see the modern chemistry can be utilized to solve the problems which were of the process which were developed many years back. So one of the step was this stage 3, which is palladium catalyzed reaction. So the phase transfer catalyst TEBA is used, which is benzyl triethyl ammonium chloride. So the issue was this was required in equivalent amount, and as such quaternary ammonium salts are they are toxic, and they should not go in liquid. So effluent treatment is required. So we wanted to avoid this issue and also to get a cleaner reaction. We screened many different things and we could come up with solution. And I'm glad to inform you that Dr. Bhausai Patil, who is a student of your college, he contributed to this work, and he could develop and optimize this condition on 100-gram scale. So now whatever substitute we have instead of TEBA is completely safe to environment and non-toxic, and it is required only in a small amount. So we could solve this issue, as well as we also have a proof of concept for the reduction of ketone to the corresponding alcohol using enzyme. We have Dr. Mahesh Patil here. So we collaborate with each other, and we are working on this step. So initial results are promising, and already there is an enzyme from Codex's company. However, they control the price, and some Chinese companies have also developed these enzymes for such reduction, asymmetric reduction. However, reliability is a little concern. So definitely we will also develop this step also for reduction using enzymatic catalyst. Currently, the process that we have developed uses this deep chloride, which is required in equivalent amount, and this is the cost determining factor for the synthesis of this montelukast using this sequence, and we are trying to reduce this cost. So in summary, this organic chemistry, as you know, through the development of many synthetic tools, it is evolving over the years, and it caters the need for sustainability through, like, instead of metal catalyst, we can use organocatalyst or photocatalyst or biocatalyst for the synthetic transformation. So several novel and practical tools are invented and applied at large scale, and industry is also ready because they have to also follow the norms of environment. There are, of course, many challenges exist when the lab curiosity, when we do it in the flask on small scale and milligram scale. When we plan to take it on gram or kilogram scale, it's not easy. It's more challenging, and it's more of a engineering as well as chemist challenge. So this tool such as organocatalysis has the capacity to substantially reduce the impact on environment, which is caused by metal catalyst, or photocatalysis and biocatalysis are the other important ways by which we can move towards better future. The last one is purely engineering aspect. Currently, most of the drugs are produced using batch chemistry, batch synthesis. But if industry moves towards continuous flow synthesis, it will revolutionize the chemical industry. The flow is not a new concept. If you look at the history, many processes are there which are being done in flow, but mostly they are non-simple chemicals, but for or fine chemicals. But for production of APIs or KSMs, this is being used in some industry, but it has not gone to the extent as batch chemistry is being pursued. So before I conclude, I would also like to, this is again the slide for new researchers or those who are currently doing research. So when we do some this work and we want to communicate with the other researchers throughout the world, we have to follow some ethics, follow some norms. So when we are writing our result in our notebook or in our journal, write what you have observed, what is the condition, write the exact condition, yield, and purity. Don't manipulate there. Even don't manipulate the data that you see, like proton 13C, HRMS, or any other data. You should not touch the data. You should not manipulate the values. And whatever work you have done, whether it is new or slightly known, partially known, give the corresponding relevant citations. You should not hide any citation. And while writing the paper or patent, or for that matter, even presentation also, you should not use the words or sentences as such from the reported literature. So the people think that whatever is available on Google is free. That is not the case. There can be they might have the rights on their images, on the content they have written. So don't copy it. Write in your own words. So that is called plagiarism. So if you copy it, when we submit to journal, the first thing they do is they check whether there is means they are following certain plagiarism means percentage or not. If it is not, it will be returned back. So if you are following all the above things which I have mentioned here, then there is no issue. Otherwise, if there is any manipulation of data or plagiarism, later after publishing, if they notice, there can be, the journal can publish a note of concern, or they can ask to retract the manuscript, which is embarrassing. So stay away from such kind of things and follow ethics in research and publication. So this is for the graduate and postgraduate, as well as professors who are doing PhD. I welcome you all to visit to NCL. You can but inform us in advance. So and for the internship, like those students who are in their master's degree second year or at the end of the first year, they can come at NCL. We have internship program here, but try to come at least 3 to 6 months. So you can apply online. There is a website for that, and approach the corresponding scientists which are you are interested, and you can come here, learn, and go back. That will help you in your career if you want to go for PhD also, and if you want to go for a job in industry also. So there, I know that from your area, students come here for preparing for the NET exam, that is CSIR NET exam for a PhD fellowship, and they stay here in Sutarwadi and Pashan and other areas without earning any money. I think that is fine for first 6 months. They should try one first attempt, but after that, with that preparation, they should also apply at NCL and join project associateship, and then side by side they can prepare for these exams. So I would like to tell you that I joined after my MSc. I joined here as a project fellow at NCL, and then during my at the end of my first year, I could qualify all GATE, SAT, and NET exam. So it is possible while working here, rather you get better idea about chemistry because you are actually doing the chemistry, so you know how it works. So for this kind of project fellow position, you can now we have online application portal, very easy to apply and attend the interview if you are shortlisted. In addition to this, there is a program called skill development. So those who have completed MSc, they can come here we have for organic synthesis, means there are many skill development programs at NCL. For organic chemistry, we have a 3 month program. We also have other programs like analytical, handling the instruments, and GC like HPLC and other instruments, even NMR. So you can join that, and that skill development fees very less amount, I think 10 or 9,000, and in that amount you also get accommodation and one food also. So those who have completed MSc can join that kind of program, and those who are interested in doing PhD, they can appear for this NET exam and any other fellowship exam. It's like Inspire also gives fellowship for PhD, and there are other also like state government, Sarthi or Bharti or many are there. So with that fellowship, you can apply online. See, this application is open throughout the year for all CSIR labs. As I said, there are 36 laboratories. So the portal is only one, but you can give your priority which lab you want to join. And there are many other options as well. As you know, IITs are there, ICERs are there, many CSIR labs are there, but you need to qualify any qualifying exam. At NCL, we don't accept GATE fellowship for sciences. Only in engineering it is accepted, but IITs also accept GATE fellowship. So finally, I would like to thank you all for giving me this opportunity and hearing me patiently for, I think, quite a long time. So if there are any questions, I'll be happy to.
Thank you so much, sir. Now I would like to request session chair, Dr. Vishnu Adole, sir, kindly take over the session.
Oh,
Dr.
thank
Vishnu
you.
Adole, sir.
Thank you, Dr. Rahul. Am I audible?
Yes, you are audible.
Oh, okay. Sir, it was indeed a very nice talk on organic chemistry. If any participant is having questions related to the slides presented or related to their research, they are free to ask. Okay. I think there is no question from the participant. Sir, it was a very nice talk, and it is my great privilege to chair this scientific session delivered by Dr. Santosh Maske, sir, Scientist CSR National Chemical Laboratory, Pune. Sir has presented an excellent, well-structured and intellectually stimulating lecture on emerging trends in organic synthesis, with the special emphasis on organocatalysis, also on N-heterocyclic carbon catalysis, organophotoredox catalysis, biocatalysis, and importantly, he also discussed how continuous flow chemistry can be applied for the synthesis of important drug molecules. They talk beautifully bridged fundamental concept with real-world industrial applications, particularly in API synthesis, sustainable methodologies, and industrially relevant transformations. The presentation stood out for its clarity, depth, and logical progression, effectively covering various mechanistic insights, reaction optimization, scalability, and translational relevance. Dr. Maskesar's ability to explain complex chemistry in an accessible manner, supported by high-quality experimental data and real research outcomes. And with this, the audience thoroughly engaged in the session not only enriched our scientific understanding, but also motivated young researcher to pursue innovation-driven and sustainable research. Lastly, important thing is that sir highlighted and motivated the participant to pursue the research in the National Chemical Laboratory. Sir, we are very thankful for your insightful lecture, and definitely the participants will have strong impression and they will pursue the good quality research in their particular fields. Thank you, sir. And I also would like to thank the organizer for giving me this opportunity to chair the session given by Dr. Santosh Maske, sir. Thank you everyone.
Thank you all. Thank you.
Thank you, sir. Sir, before concluding this session, I personally have one question. Can I ask?
Yeah, sure. Please go ahead.
Okay, sir. Okay, sir. Which type of compound can be used as a pre-catalyst? Just you have given palladium triphenyl phosphine as an example. Is there any other types of compound that can be used as a pre-catalyst?
No, this is the general term. You can hear me? Can you hear me?
Yes, sir.
पप्पा तुमच्या मोबाईल मध्ये काय पण दाबतो.
Yeah, actually, this is a general term. Pre-catalyst. Pre-catalyst means any catalyst in its pre-form, means it's in stable form. For example, I gave that palladium tetrakis as the example. So the actual species which is working in the reaction is palladium triphenyl. So the pre-catalyst is tetraphenyl. So what happens is when it goes to the solution, one of the ligand goes away, and that is the actual species. So that's why it's called pre-catalyst, means before actual catalyst is formed, we can store that substance in, means it is bottleable, basically it can be stored and used when required. In that case, the actual catalyst will not be stable, we cannot store it, we cannot use it or weigh it and handle it in open air. So that is one example. The other example that I gave was NSC. So NSC carbene is not a stable species, which actually act as a catalyst, organocatalyst. So it has to be generated in situ. So the pre-catalyst in this case is its corresponding salt. So the salts are stable, even air stable. Whenever you want to do NSC reaction, we can take this pre-catalyst, which is a salt of that heterocyclic moiety, and treat it with base. So basically what we are doing is we are generating the catalyst in the reaction. So that it remains stable and it performs its catalytic activity. There are other substances or chemicals like arines. You might have heard about arines. So arines are not isolable compounds. So to generate them, we can keep the substrate in such a way that they are stable. But when we keep it in the reaction with along with other reactants, we can easily generate, and without isolation, we can react with other species. So that's free form of any substance. I hope I have answered your question.
Thank you, sir. There is one more question from our research scholar. You told about the
You are not audible.
Hello.
Yeah.
Now it
No.
is audible, sir.
Yeah.
Okay, sir. You told about the plagiarism. There is question from our research scholar. There are different types of software that use for the detection of plagiarism. The question is on what basis that software detect the plagiarism? Because most of the students having projects for their PG courses also.
Yeah, right. So whenever you copy something from open sources like Google or any electronic book, so they also have this all the information stored with them. For example, I think it is the software. So when you copy and paste your data or whatever you have written in their web portal and submit it, so it can detect that which part of this paragraph is taken from a book, a particular book or journal or patent, and it shows that corresponding reference also.
Okay, sir. Thank you. Now, on behalf of organizing committee of Department of Chemistry, MSG College, we express our sincerely thanks to respected Santosh Maske sir for giving excellent talk on the organic synthesis and related topics. I also Thanks to session chair Dr. Vishnu Adole for chairing this session very expertly. Thank you once again. Now,
Okay.
with the kind permission of coordinators, we concluding this last session of the day. Now we are moving towards the poster presentation. Thank you, sir. Poster and oral presentations. Those participants which are interested for the offline oral presentation, go to hall number A3. For the online oral presentation, list has been posted in the group. Instruction related to that will get soon. Those participants are interested for online poster oral presentations, be in touch with us. We are starting this oral presentation online very soon. Participants will get divided into 2 slots. At a time, there will be presentations for the 2 candidates. You will be admitted accordingly. Wait for 2 minutes. Don't leave this session.
नंबर काही लागले नाही. आता demand
Sir, hello.
India. Then he have a number of awards on his name. He is recognized as a guide of PhD and MPhil of Savitribai Phule Pune University. He is honored with the number of awards such as the Scientist Award from 1924 by National Environmental Science Academy, New Delhi. Again, he was honored with the Young Researcher Excellence